Okay, so let's officially start. Hello, everyone. Welcome to the fifth edition of our Quantum Machine Learning Conference. This is a conference organized by Quantum AI Foundation, or Fundacja Quantum AI in Polish, and Q Poland. So Q Poland is a Q cousin of the international organization that is called QWORD. So our goal is to build the open global ecosystem for quantum technologies. We started organizing this conference a few years ago. It's always in the online format, and hope that you will enjoy this edition as well. So, as you can see, we are recording the conference. So, hopefully, the video recording will be later available on our YouTube channel. This is the plan for today. So I will start by giving the introduction to quantum machine learning. So actually, we assume that all the participants have at least a basic knowledge of quantum computing and machine learning. We had to assume something at the beginning. The other talks will be more advanced, but I decided that it's good to give an introduction and at least to just recall some basic, most important concepts. Hopefully it will help you understand the other talks as well. So this will be at the beginning, and then Jacob Cybulski, who is available already, who is already with us, will tell about measuring and interpreting the states of temporal quantum models. And then Sebastian will follow up and tell about data preparation for quantum encoders. Then Akash Kundu will tell us about KANQAS, the implications of Kolmogorov-Arnold networks in quantum domain. And then Artur Miroszewski will tell about the cost of quantum kernel methods, insights into resource estimation. Then Nouhaila Innan will tell about exploring quantum machine learning and quantum federal learning for financial fraud detection. The next talk will be given by Tomasz Rybotycki about automated quantum machine learning as hyperparameter optimization problem. And finally, Krzysztof Pomorski will give a talk about quantum neural network implementation in semiconductor single-electron devices. So this is the plan. So each talk is scheduled for 30 minutes. So there will be, so actually the talks should take about 25 minutes, and we'll also try to have at least 5 minutes for Q&A. Um, and if you have any questions during the talk, first of all, please post your questions on the chat. So during the Q&A session, we'll try to read them. And you can also later during the Q&A raise your hand and interrupt. If there is something really urgent, you can also try to raise your hand during the talk, but the recommendation is to keep the questions for the Q&A just to be sure that we'll keep the intended schedule. So without further ado, let's start. So quantum machine learning. So what is quantum machine learning actually? Actually there's still no, let's say, consistent agreement between the scientists how to interpret the domain of quantum machine learning. Because actually there are different approaches to, let's say, to the doing science and the connection of quantum computing and machine learning. So in general, the quantum machine learning is the intersection of quantum computing and machine learning. But some people consider quantum machine learning only as the application of quantum algorithms or quantum technologies to the machine learning. So this part is sometimes also referred to as quantum enhanced machine learning. So classical machine learning enhanced by quantum computing. This nice image is taken from a lecture given by Maria Schult about quantum machine learning and Penelane. And she divided the whole domain into 4 parts, depending on whether we use classical or quantum algorithms and whether we use quantum or classical data. So this quantum enhanced machine learning that we'll mostly focus on during this conference is somewhere here. So we use quantum algorithms on classical data. But it's always good to know that we can also try to apply classical machine learning algorithms to quantum problems or quantum data. In my opinion, it can be even more successful, at least in the nearest future, and there are already such applications of classical machine learning to solve some quantum problems. And of course, we may try to apply quantum algorithms to quantum data, and in the long term, it's also believed to be quite successful. So quantum algorithms are natural, or seem to be natural tools to tackle problems related to quantum data. And of course, here we have classical machine learning, right? So classical machine learning algorithms applied to classical data. So I will start from this part, right? So applying quantum algorithms to classical data. So there are different approaches to do this quantum enhanced machine learning, but currently one of the most popular approaches are based on something that is called variational quantum algorithms. So these variational quantum algorithms share a common structure where a task is encoded into a parameterized cost function that is called the ansatz. So it's a parameterized quantum circuit that is evaluated using a quantum computer. And there is also a classical optimizer that trains the parameters in these variational quantum algorithms. So usually here, as the circuit is parameterized, we also need parameterized quantum gates. So usually there are some kind of rotation gates. And this approach emerged as the leading strategy to obtain quantum advantage on noisy intermediate scale quantum devices, so contemporary quantum devices. And I will later tell why this NISQ or this approach is or seems to be suitable for the NISQ devices. So coming back to the ansatz, so I said that it is a parameterized circuit preparing the quantum state. So some ansatz architectures can be generic, but there can be also problem agnostic problem agnostic, but there can be also architectures that are problem inspired. So in many cases, one can use information about the problem, the optimization problem, usually the optimization problem that we have to tackle to tailor an ansatz. And this is let's say, a typical decomposition of such an ansatz. So this parameterized quantum circuit. So, in general, in quantum computing, the quantum gates correspond to unitary operations. So here we can also decompose the ansatz into a combination of unitary operations. So in general, this unitary operation parameterized by a given set of parameters can be expressed as a product of L unitaries sequentially acting on an input state, and each unitary can be decomposed into a sequence of parameterized and unparameterized gates. So this decomposition is represented here. So in this case, this Wm is an unparameterized unitary, and Hm is a Hermitian operator. So this is a general architecture of these variational quantum algorithms. And a few words about the cost functions that are computed using such a parameterized quantum circuit, the ansatz. So its minimum should correspond to the solution of our optimization problem. It's useful to have the cost function that is operationally meaningful, so that smaller cost values indicate a better solution quality. It should be possible to efficiently estimate it by performing measurements on a quantum computer and possibly performing classical post-processing. An implicit assumption here is that the cost should not be efficiently computable with a classical computer, as this would imply that no quantum advantage can be achieved with the variational quantum algorithms. And of course, this cost function must be trainable, which means that it should be possible to efficiently optimize the parameters of the ansatz. So what the quantum processing unit does in this pipeline, so given a set of parameters, it returns a set of measurements. And what a classical processing unit does, given a set of measurements from the QPU, it calculates the energy value, so it's usually some kind of averaging. It performs the optimization procedure, it calculates what a new set of parameters should be, it checks whether we have reached the minimum, it makes sure that we don't make more iterations than we should have done, and so on. And these are just examples of some classical optimization algorithms for this. And actually choosing a right optimization method for a given problem is critical, as it decides whether we'll succeed or not. And it's pretty difficult. So in some sense, it's science, but it's also an art. So there are no silver bullets here. And now, why these variational quantum algorithms are good for the NISQ devices? So what are the main disadvantages of these noisy intermediate scale quantum devices that we have nowadays? So there is a lot of noise. So every time we apply a quantum gate or do a measurement, there is a substantial chance that we'll actually apply a different gate. And this is just one of many flavors of the noise that we can get. And in addition, the qubits don't live for too long. So after some time, there is a decoherence, and we can be pretty confident that whatever information was stored in the system, it is lost. So the number of operations we can perform in this time is limited. We don't have many qubits, of course, and there might be some restrictions on which qubits can interact with each other. So these are just some disadvantages of the contemporary quantum computers. As a consequence, there is a set of restrictions for this quantum circuits that we can design. We can use small number of operations per qubit. So this is called the circuit depth. We can't assume everything will go according to plan and there will be no errors along the way. But even if there are errors, we should still get a reasonable answer. Yeah, so we call this robustness. So we would like to get a reasonable answer. So that's why we need to design our circuits properly. And obviously, we can't use more qubits than we have, which is an important limitations nowadays. So now, why these variation quantum algorithms are good for the NISQ devices then? These algorithms are pretty flexible when it comes to the circuit depth. So we can use a pretty simple ansatz if you want to keep our circuit very shallow. But once we have a machine which allows for a deeper circuit, we can use more sophisticated ansatzes and the performance might increase as a result. And these variation quantum algorithms have shown to be somewhat resistant to noise. So even in the presence of noise up to some level, it can give the correct results. And some researchers even claim that a pinch of noise might help with the optimization process because it helps to escape local minima. So it can help with ensuring generalization of our models. Whether it can lead to a quantum advantage is still an open question. Some researchers say that perhaps we could also try to simulate this quantum noise classically, but we also know from some other research works that not every noise from a quantum circuit can be efficiently simulated using classical computers, so perhaps it could give some advantage at some point. And these are just examples of the variation quantum algorithms like QAOA, quantum approximation optimization algorithm, and variants like recursive QAOA or warm start QAOA, in which we start with a suboptimal solution and try to improve it. There is also variation quantum eigensolver, and there are also some variants like filtered VQE or layered VQE, and could be also a combination of both. So these are just some examples of the variation quantum algorithms. But there can be also quantum or hybrid neural networks in which you might have classical nodes, classical neurons, and quantum nodes. And these quantum nodes, again, could be just simple quantum variational circuits, parameterized circuits, right? So in this case, these are the parameters. So as in the classical neural network, we have a set of parameters that we would like to tune to minimize the cost function at the end, right? So this is the goal. And we can also compute something like a quantum gradient in this case, because if you are familiar with classical machine learning and classical neural networks, then you know that in order to train the neural networks, we usually use a backpropagation algorithm. So of course there could be other algorithms as well, but the backpropagation turned out to be one of the most successful algorithms, and indeed it is based on calculating the gradients gradients of the loss function over the parameters. And in this case, we also would like to calculate a gradient, something like a quantum gradient, by just slightly disturbing the values of the parameters. There are ideas to combine both, to combine hybrid neural networks or quantum neural networks with variation quantum algorithms. There is a nice paper that was actually based on a master thesis prepared by Justyna Zawalska about solving the traveling salesman problem using TensorFlow Quantum. And in this work, she combined the quantum QAOA algorithm with hybrid neural networks indeed. There might be also some other approaches to quantum enhanced machine learnings, like quantum support vector machines with quantum kernels. So in general, in support vector machines and quantum methods, the kernels are functions mapping input data into a higher dimensional feature space using a kernel function, which enables linear algorithms to perform nonlinear computations. So of course, there could be some classical kernels, but we can also think about quantum kernels as well. And in some research works, it was reported that adding these quantum kernels or quantum layers can also give an advantage, at least in the experiments, because in general it's difficult to prove the advantage of proof that we cannot build something better, but at least experimentally it has been already demonstrated a few times that at least that adding some quantum layers can improve some results, which doesn't mean that there cannot exist better classical algorithms, of course. All right, so that was about quantum enhanced machine learning and using quantum algorithms to classical data. But we can also think about using classical machine learning algorithms to quantum data or to improve quantum algorithms. And here are just some examples, like quantum state tomography, which is a process by which a quantum state is reconstructed using measurements on an ensemble of identical quantum states. There's also quantum feedback control and quantum circuit optimization. It's usually done using classical reinforcement learning algorithms. And if you are interested in such applications of machine learning to quantum sciences in general, there is a nice review article about or titled Modern Applications of Machine Learning in Quantum Sciences. It's quite long, but I can highly recommend it. And there's also an interesting approach to use classical machine learning to improve quantum algorithms. Because if you are familiar with solving combinatorial optimization problems using quantum algorithms, then you have probably heard about something that is called QUBO, quadratic unconstrained binary optimization. So it is a mathematical formulation of our optimization problem in which we want to find an assignment of multiple binary variables of degree at most 2 that would minimize our cost function. And usually this cost function is a combination of the objective function that we actually want to minimize or find a minimum, but we want to find a minimum satisfying some constraints. And usually satisfying the constraints means that some formula, some expressions should be equal to 0 for our optimal assignment. And in order to ensure it, we usually construct a similar formulation in which there is the objective function that we want to minimize, and there is another quadratic binary formula corresponding to satisfying our constraints. And there is a parameter that is called a relaxation parameter. And when values of this parameter are very high, then our solvers, our optimizers, will ensure that all the constraints are satisfied, because these values here cannot be greater than 0. So all the constraints are satisfied. All these expressions should be equal to 0. But on the other hand, when we decrease the value of the relaxation parameter, it could be easier for the optimizer, for the solver, to find good assignments for our objective function, to minimize our objective function. But at the same time, there is a non-zero probability that some constraints are not satisfied. And now the question is how to find the best value of the relaxation parameter to have a good trade-off. So to have a high probability that the solution will satisfy all the constraints, and at the same time to ensure that our solver is able to find a very good solution, right? So there is a trade-off, because if the value of the relaxation parameter is too high, then this part dominates, so it's more difficult for the solver to find a good value of good assignment for our objective function. And the good value of the relaxation parameter could be found using machine learning techniques. There is a nice paper on how to do it that is titled QROS, QUBO Relaxation Parameter Optimization via Learning Solver Surrogates. So this relaxation parameter is, as I explained, is a coefficient regulating the quality of the result and the probability of obtaining a correct result for quantum computing. So in the original paper, the goal was to train machine learning algorithms, classical machine learning algorithms, that return a good value of the relaxation parameter for a given problem instance. And the problem that was solved then was an instance of the traveling salesman problem. And first, they generated very large data set for different instances of the graph for the traveling salesman problem and different values of the relaxation parameter. Then these instances were solved using a quantum algorithm, and then based on the solutions, they trained classical machine learning algorithm as something like a surrogate function that was able to give the probability of obtaining feasible solutions and the quality of the solutions for totally new instances of our input graphs for TSP and other values of the relaxation parameter. So there was a nice optimization strategy involved. So by summarizing the quantum algorithms, I can tell you that I have already heard about research papers in which quantum counterparts or quantum variants of multiple classical machine learning algorithms have been published. So recently, I've even heard about quantum large language models. Of course, there are also such approaches. Not all of them are reasonable, of course, but and actually it's still an open question when exactly we could get an advantage. Some other examples of application of quantum algorithms to classical data. So we can use quantum machine learning for Earth observation. So for example, the quantum support vector machines are sometimes used for this. There could be also quantum machine learning neuroimaging for Alzheimer's predictions. So of course, the natural question is, can this quantum enhanced machine learning achieve good results in some learning tasks? So definitely yes, we already have some proofs in research papers. And another question, can quantum enhanced machine learning outperform classical machine learning? Perhaps, but first of all, it's probably still too early because the experiments that have been carried out were in relatively small scale. And even if we outperform classical machine learning algorithms, it's difficult to prove that it's really an advantage. But in general, even in classical machine learning, it's difficult to prove anything. But for sure, it's an interesting research area. So can we achieve, or do we already have quantum advantage in machine learning tasks? The first article that claimed that we might actually have achieved something like a quantum advantage in machine learning task was released by researchers from Google. And basically they said that they showed that quantum machines could learn from exponentially fewer experiments than the number required by conventional experiments. So it doesn't mean that the accuracy of quantum machine learning models was better, but just the size of the training set was much smaller. So this is also important because sometimes it's very difficult and computationally expensive to generate large data sets. So this kind of advantage could be also interesting and very useful. Later, there was another paper last year released by researchers from IBM in which they also claimed that there could be something like a super polynomial quantum advantage for approximating combinatorial optimization problems using computational learning theory. So, there are already such publications, and as for now, it's in some experiments, it have been demonstrated that we can get some advantage, but as I said, we cannot prove that there are no better classical algorithms for sure. So this is one of the problems. So now going to the practice a bit at the end, I wanted to tell you about a few libraries or frameworks for quantum machine learning. So the most popular one is probably Pendelane, which was also the first library for quantum machine learning, and for this reason, it was named that it is TensorFlow of quantum computing, until Google released its own TensorFlow quantum library. So here you can see just a parameterized circuit with two parameters, and it was a relatively simple ansatz, and there was a cost function and method for calculating the gradient. As I've told you, at some point Google released TensorFlow Quantum. So it's another quantum machine learning library. So we can see that there's another parameterized quantum circuit. And Qiskit. In Qiskit, there is also something like a quantum machine learning model. So if you want to learn more, of course, beside attending this conference and following our lectures, our talk, you can also watch a very good lecture given by Maria Schult, which can give an introduction for quantum machine learning. Maria also co-authored a very good paper about an introduction to quantum machine learning. There are also many useful resources on the website of the Quantum AI Foundation. There is also the EDX course prepared by Peter Witek. It's also available on YouTube. There is a nice summary of variation quantum algorithms. There is a nice literature review on quantum machine learning and its applications. And of course, there was earlier that I also mentioned about the paper on using classical machine learning to quantum sciences. So with this, I thank you for the attention. We still have a few minutes, 3 minutes actually, to the next talk. So let's see if there are some questions. And if you have any questions, feel free to post them here on the chat, or you can also raise your hands. I saw that there was, yes, there's a question. Do we know which types of classical problems can be useful for quantum algorithms? So in general, most of the algorithms that are presented are good for solving combinatorial optimization problems. So when we have optimization problems, then this, let's say, variation quantum algorithms could be suitable to solve them. But on the other hand, when you think, so the traveling salesman problem is also an example of the optimization problem, actually. But when you think about quantum SVMs, then something like a binary classification is a good use case. So actually, and as I told you about this quantum algorithms for Earth observation, indeed the researcher used binary classification based on quantum support vector machines. So there is another question. At present, what are the advantages of QML over classical machine learning? One you mentioned that QML needs smaller data sets. So regarding the smaller data sets, it's also not always the case. So it was just the case of this research published by Google, of course, that they showed that the quantum machines could learn from exponentially fewer experiments, but it doesn't mean that it's always the case that the quantum algorithms can be trained on a smaller data set. So as for now, it's still an open question when exactly we can get an advantage, because you know, as I told you, at least in the research articles that I'm familiar with, the researchers reported that in some experiments they obtained some advantage, but they didn't prove that there are no classical algorithms that could be better. And I'm pretty confident that there could be some classical algorithms that could perform at least equally well. So it's probably there's still no serious advantage, but we'll see, because you know, in general in machine learning, when we train machine learning models, so all machine learning is all about optimization. We usually have some kind of loss function or cost function that we would like to minimize. So we would like to find a set of parameters that minimizes our cost function on the train set, right? And as I've told you, these quantum algorithms could be suitable for solving optimization problems. So in general, there is a chance that once we have larger quantum machines, they could be also used to enhance the process of training classical machine learning algorithms as well. But as for now, it's still an open question. There's another question from Jacek. Quantum process can be simulated classically. So quantum approaches can only have advantage in terms of computational efficiency. Yes, actually, there can be only advantage in terms of computational efficiency, but also it could be advantage in terms of the smaller data set, for example, right? Like Google demonstrated. But it doesn't mean that we'll be able to solve some problems that we cannot solve classically. So we can do it or taking into account that maybe currently some problems could be just computationally infeasible to be solved classically. And that's why potentially we can get a quantum advantage. There is a question from Ravi. Do we know which types of classical problems can be used for quantum algorithms? So yeah, there was already this question, so I already answered that. I think QML could be faster than classical. Can be. We'll see. Perhaps there could be an advantage if in time of inference or time of training indeed. So thanks, Maturian. Thanks for pointing that. I do not see more questions, and actually it's also time for the next talk. So with this, I will stop sharing my slides now, and I will give a floor to Jacob, and perhaps he can also answer some of the questions because he's also working on some interesting applications of quantum machine learning. So Jacob, let me see if you can share your screen.
At the moment, the host disabled participant screen sharing. That's the message I'm getting.
All right. How about now? Can you share it?
Much better.
All right, good.
Yep, the wrong screen, is it?
Yes, I can see it.
Yep. Okay. Okay, so welcome to my talk. The original title was Measuring and Interpreting the States of Temporal Quantum Models, or TQM. Halfway through the presentation, I thought, well, it's slightly getting into a larger topic. So I thought a different title, Why Temporal Quantum Models, TQMs, are so damn difficult to train. They are interrelated because it's all about measurement. A lot of it is about measurement, but there are other issues which pop up when developing time-based models. So about me, I run a small consulting company in quantum computing, quantum machine learning in Melbourne, Australia. I'm also honorary associate professor at Deakin University in Australia, also working with students on quantum topics. The main issue here is the problem of time. What is time, how it's related to quantum computing? I wanted to start with a big bang and start talking about quantum mechanics and gravity and other things, but I thought the reason says let's focus on quantum computing. Quantum computing, similarly to quantum mechanics, takes a very pragmatic approach to time, which means it considers time as an external variable, which is presiding over changes in observable phenomena. When you talk about gravity and general relativity, we have a lot of complexity about speed and black holes. We're not talking about any of that. Our universe is flat and we don't get anywhere near black holes. And the time ticks like our watches. So the notion of time is very much classical. So we can develop quantum computing models, we could train them, and so they could focus on processing time as can be encoded in data, and then eventually that data will have to appear as part of the model structure. So we have a couple of examples of how time can be embedded into a model. On the left-hand side below, you can see the function fitting data, where the data is identified by position in time, and the fitting function could identify the value. On the right-hand side, we have a sliding window protocol. And in this case, the sliding window is moving along the data set. And basically, we take a timeless approach where we try to relate the past data to the future data. So very, very simple, very much what happens in classical examples. So if you want to develop a quantum model which represents and manipulates time-related data, there's a lot of them around. Some of them, they could process time or temporal data directly, such we have sequence models like RNNs, LSTM, GRUs. We have reservoir computing, which has been developed specifically for temporal data. We can talk about self-attention and transformers, even large language models, as well as Fourier analysis with the partial Fourier transforms of fast Fourier transforms. And we have all quantum equivalents to what's well known in classical machine learning. We also have lots of algorithms which look at optimization, the change, optimization of the model parameters. They could be also optimization of the phenomena we represent. So optimization algorithms, we also have quantum annealing, quantum adiabatic algorithms, reinforcement learning, Bayesian modeling, genetic algorithms. So we have quantum equivalents of those as well. We have also a lot of standard models, quantum neural networks, support vector machines, kernel methods, clustering algorithms. They've been all used before to manipulate temporal data. Okay, so we have lots of applications of those. We could find them in science and engineering, earth science, finance, medicine, and they focus on different tasks. One of them is explanation of the past. Given the sequence of the past data, if we could fit a function into the past data, we could then explain what was happening in the past, how the data was moving as explained by a particular function and its properties. Definitely, we have a lot of work in decision support, where we look at the sequence of data from the past, and we want to make a decision about some aspect of whether it's a machinery or the process or manufacturing. So it's a sequence to logical mapping. A lot of applications in forecasting, where the past data will be used to predict future, and stochastic approaches, random walks and Monte Carlo approaches, where the constraints in a given area could be captured, for example, in a stock market, and those constraints could be used to generate random prediction of the future, and from those or multiple thousands of those predictions, you could identify the likely scenario in the future, like the value of the stock. And then we have applications in noise and anomaly elimination, where there would be a mapping from sequence to sequence. Why I'm talking about it, I want to really draw attention to the fact that in all those applications, there are some specific mappings between either sequences of data in the past to a sequence of data in the future, or individual data points in the future, or the data points in the present, or even sequence to sequence or sequence to constraints. So this indicates the nature of the application, and the model needs to respond to those requirements. A lot of issues are with processing time. One is that time data has some unique characteristics. First of all, the features of the data are not present visibly in the data. The features of a time signal are outside. They have to be interpreted. We need to identify patterns in the sequence of data to really understand what's happening there. Usually we deal with high volume of data. There's also some continuity between neighboring data points, some cyclicity or seasonality in data. There's always some noise present, anomalies, and even very volatile situations. So the data is specific. And the good thing is that there's a lot of classical approaches which excel in processing that type of data. So it's actually a difficult task for people in quantum area, because classical approaches are phenomenal. There's years and years of experience that have been put into building classical models to process time-based data. That also means that when we attempt to apply quantum techniques to such tasks, we aspire to handle much more complex cases, non-trivial cases. For example, in anomaly detection, we are trying to identify features and anomalies which are not obvious. So like in change in the pattern of the time data, rather than a simple phase difference or amplitude jump in anomaly. We also tend to generate large models, large circuits to capture all the complexity. And that's not good for quantum machine models. The capacity to learn is questionable, and usually training those models is quite difficult. Also, they give high error rates on noisy machines. Also, there's a lot of new work done where people look at the cases where quantum machine learning was successful, and they pick up the situations and the approaches from those quantum approaches, and they translate them into classical algorithms, and with great success. Now, about the measurement. Obviously, when we deal with time data, we need to be able to encode it into the model, and we need to be able to decode from that model. And that's not difficult. First of all, let me introduce some terminology. At the very top of the slide, you can see some measurement configurations. Number one is when we measure all qubits. That's usually called the global cost measurement. Or we could measure one or just very few qubits. That's a local cost measurement. We could also have measurements which are segmented into groups, and those measurements could produce values for separate variables. So we have this flexibility. Now, when we measure all qubits, it doesn't mean that they will return multiple values. It just means that we measure multiple qubits, but then the results from those qubits could be analyzed, and we could produce a single value. Like we could use the parity of cat values, like number of ones, and from that we could determine whether the outcome is positive or negative. So that sorts out the physical aspect of measurement. Now, what we can get out of those measurements? And I mentioned, like if you have a single qubit, the second row on the right, that single qubit, if the measurement is repeated multiple times, we could determine the probability of outcome 0 or outcome 1, and based on the distribution, we could determine a logical outcome, the Boolean, true or false. That's one out of the way. How can we get integers and float numbers from measurement? First of all, let's look at the distribution. So if you want to produce a distribution of different outcomes, this is, for example, what we do with quantum graphs. With Sebastian, he's talking next. We are actually interested in a whole distribution as an outcome that we could process. But if you want just a single value, which comes from the probabilistic distribution as measured from the quantum circuit, then we could look at the height of the bar, the most likely outcome. That height of the bar, it's a floating point number. If you want to get a specific value, like integer value, the cat representation, which is the combination of 0 and 1s from the qubit measurements, that will give you integer. So we could get and interpret the results in some way so that it's very much like what we do with in classical situations. What if we wanted to get the whole sequence of data coming from the measurement? You may be familiar with amplitude encoding when you have multiple values on the input. The amplitude encoding can pack all those values into sort of a distribution of values. And when we measure all qubits, the measurement could give you, for example, the probabilistic distribution, or it could give you expectation values. So expectation values could produce positive and negative numbers. They are simply eigenvalues of the qubit measurements. And so we could actually train the model to produce those expectation values with specific characteristics. So we can put a sequence on input using amplitude encoding or some other technique, and we could get a sequence of data on output. It's limited in terms of the number of qubits that we have to our disposal. Or we could produce multiple models which generate different parts of the sequence. So we can have the whole lot of possibilities. We can represent and measure almost anything using quantum models. Now, how do we go about training temporal quantum models? And what are the problems with that? As in the previous talk, we found about variational quantum algorithms, and so we're not going to talk about that anymore. But let's consider a model similar to QNN, which deals with time. In fact, it's an issue which relates to any quantum model, not necessarily temporal quantum model. The way we would like the model to work is that on input, we're going to have state preparation. We encode some data. And on output, we have state measurement. And the state measurement will produce output data. So we pack classical data into the model, and we expect it to get some data out of the model. Now, the interesting thing, what happens inside, of course, we have this variation quantum model optimization with most likely classical optimizer using classical loss function. What should be happening in the middle? You could think in terms of deep learning systems that at the layers, at different layers, we have some abstraction of data appearing on input. And we could expect the same happening in a quantum model. If we measure what happens in between, there would be some similarity to what we get in deep learning systems. However, at some point, we need to have some representation of the problem and some representation of the solution that we expect on our output. And in the middle, we would have the exponentially large state space, which is mapping problem to solutions. And this is where the advantage is happening. And this is where what we don't want to immediately measure because it's very highly dimensional, exponentially high dimensionality here. So this exponentially high dimensionality would allow, for example, linear slicing through the data to separate quantum information. So this is the place where quantum advantage is happening. However, the quantum model at this point produces so many likely solutions that they are quite useless to us. We need to be able to scale them down and prepare on output only a few solutions. So that's more or less what happens. What is the issue with that type of thinking? First of all, the high dimensional parameter space. That means your circuit has a lot of operations, which such as rotations of qubit states, which are parameterized, and they act in a similar way like connections or weights in a traditional classical neural network. So this is actually great, enables linear separation of quantum information in that high dimensional space. But at the same time, it flattens the gradient space. So the optimizers find it difficult to navigate towards the minimum. I'll talk about that in the next slide. It's also, we have highly entangled circuits, which is great because that gives you the rich representation of data. Entanglement is key to quantum circuits. At the same time, highly entangled circuits, they suffer from non-local gradients. What does it mean? It means that through the entanglement, the change in the parameter in the remote qubit will have an impact on the parameter, on the rotation of another qubit. So the gradients are going to change in a non-local way. That connection between qubits upsets the whole idea of optimization of gradients. So that's an issue. That results also in very complex state dynamics, and quite likely it will give you the cost landscape, which is very unintuitive. Also, because of the dependency between qubits and the operations, we have high decoherence rate. So we have pros and cons. The global cost, measuring of all qubits, is great because it gives you better utilization of parameters, training parameters. If you measure a single qubit, it means that parameters associated with other qubits are not utilized so heavily. The parameters are not being changed so intensively. So that's great. At the same time, it requires exponential increase in the circuit runs. We need a lot more runs, in fact, exponential number of runs to prevent the sparse distribution of outcomes. I'll show that in the next slide. Then model initialization. The quick and easy, the most popular is random parameter initialization. You have done it yourself, I bet. At the same time, it's been proven to make model optimization ineffective. I'll show it next. All of these issues shown above are said to attract barren plateaus. So barren plateaus is the evil. What are barren plateaus? Okay, there's a lot of literature on barren plateaus, including my article, which is somewhere here. But I think there's a lot of misconceptions about what are the reasons for barren plateaus. The main reason is the curse of dimensionality. Okay, what does it mean? It's nothing to do with quantum systems. It's just something to do with the space, which is defined in multi-dimensional way. So let's look at on the left. I have here the depiction of two circles. On the left, it shows a four-dimensional space. It's just a metaphor, of course, because it's on 2 dimensions. And on the right-hand side, we have 45-dimensional space. Let's assume that they are so-called n-balls. N-balls is a two-dimensional, two ball is a balls in 2 dimensions, a circle. The 3-dimensional ball is a sphere. The 4-dimensional ball is the sphere in time, perhaps, and we could extend it further. And the interesting thing what happens is that as we increase the number of dimensions, the balls, the volume of those balls is shrinking. This is bizarre. Intuition says the more dimensions we have, the volume should be growing. It's just opposite. So if we have a low dimensional space and we were measuring and trying to produce the cost surface, the cost landscape in that 4-dimensional ball, there's plenty of space for the surface to float up and down, and the gradients that are leading towards the optimum are quite high. If the space starts shrinking, as depicted here, the gray area, the surface is squeezed and the gradients are approaching 0. In such cases, the optimizer has very little chance to find the optimum, especially if there's noise from quantum computation. If the noise is exceeding the gradients of the space, of course, we can never find the optimum. Also, it's important where you place the optimization initial point, the initialization of the quantum model. Ideally, we should put it very close to the optimum. If we put it far away, it's in a high-dimensional space, the optimizer has very little chance to find the path down towards the optimal solution. That's actually shown here. I ran a little experiment. I produced the n balls from 1 to 100 and tried to give the density curves of distribution of pairwise distances between points within the ball. The high dimensionality, you can see that all the distances get cramped around the mean, which means that virtually all distances between points in high dimensional ball are constant. That means the space is flat. So that's a barren plateau. So once those dimensionalities are linked to parameters of the model, we know it's a problem in quantum models. And because the dimensionality grows exponentially, we have exponential problem here. Now, what about measurements? What happens when we have too many measurements? So if we add a single measurement to the current architecture of the quantum model, that doubles the number of outcomes on output. Well, that's one. If we have all qubits measured, that means we have 2 to the power of n outcomes on output. So that means we need to exponentially increase number of runs. If you don't do this, that means you're going to get the outcomes which are not populated with data points. And if you want to calculate probability distribution, you have incredibly imprecise calculations. And that will have an impact on the optimizer, virtually all operations on your quantum model. So this should explain why barren plateaus exist. So we need to rethink the whole approach to temporal quantum models. And the main thing is to create very frugal model design, which means reduce number of qubits, reduce number of layers, parameters, remove unnecessary entanglements, remove measurements. Or this is actually a phenomenal problem with the new generation of quantum machines. Everybody wants to have more qubits. More qubits, more measurements, more complexity, more runs. It's an issue. So we need to be very frugal about that. We need to start refining parameter initialization. Do not use random initialization because that places the starting point far away from the optimum. You need to have different strategy about model initialization. Use gradient-free optimizers. Don't use Adam and Nadam. Start using particle swarm optimization, evolutionary or Bayesian optimizers. You could also rescale the gradients. If you use the gradient-based optimizer, you could use also quantum-aware optimization. For example, the quantum natural gradients is the whole approach of creating optimization which understands what happens in quantum models. We could also redesign the model. We could use BP-resistant models such as quantum convolutional neural networks. That's because the complexity of those models lies not in the entire model, but in the mask or the filter which scans the data. We could use barren plateau resistant model design. For example, we could develop the model layer by layer, adding small number of parameters at a time. There's lots of techniques, regularization of the loss function, gradient clipping, mid-circuit measurement to break the dimensionality, and we could use hybrid models, such as hybrid reservoir model. If all fails, you could turn to analog solutions or classical solutions like analog Rydberg atoms, neutral atoms, cold atoms, quantum annealing, adiabatic quantum computing, and there's nothing wrong with classical approaches. Like you can't beat fast Fourier transforms. It's simple and it works every time. What I show you here is a clever way of using the reservoir models. The reservoir models work the way that you take input and you lift it to exponential or to high dimensional space, like what you do with kernel methods, except that you use a model, machine learning model, which is lots of parameters, but those parameters are randomly initialized, which means there's no training of them. So once you expand dimensionality in quantum modeling, you could do it exponentially. Then you could use very simple linear model, classical model like ridge regression to find a solution. It's an amazing approach. It works amazingly well. So we simplify the quantum model, and then we could use a very simple classical model in combination with the two. So that takes us to the end. I hope I'm not over time. My current work with Sebastian is on quantum graphs, and I'm interested in dynamic quantum graphs, how the phenomenon such as social network changes over time. He's interested in emerging communities, and so we're having a lot of fun. So thank you. Any questions?
Thank you, Jacob. All right. We have maybe 1 or 2 minutes for questions. Let's see. I do not see questions on the chat, but maybe someone would like to unmute and ask. Oh, there's a question from Artur. When encoding time series data using amplitude encoding, what happens to the time itself? Is it also encoded or not?
Okay. Well, if the data value is representing data points that you're encoding in the amplitude encoding, if it's time related, that means that time is encoded into the circuit, obviously. So yes, the time is not lost because the time actually is in data, and that data gets encoded, and that data is used for training.
Mm-hmm. Good, thanks. I hope that it answers your question, Maturam. Do we have more questions to Jacob? this is the last chance, but Sebastian will have a follow-up talk, as far as I understood. So Sebastian will could also maybe take some related questions. Thank you, Jacob, once again.
Thank you.
Sorry, there is another question from Artur. Does measuring all qubits have an advantage over measuring only a few selected qubits? Are the results the same?
Well, it depends what you do. So if you measure all qubits, first of all, you expect to get exponential number of outcomes. Okay, so if you want to get the result, which is a single value, that makes no sense. That makes a lot of sense if you want to get probabilistic distribution of outcomes, if that's the result you're interested in. But the more measurements you're going to conduct, the more runs or shots of that particular circuit you need to involve. Okay, so if you have 8 qubits and you add 8 measurements, you need to get 2 to the power of 8 outcomes. You need to populate them with results. So if you have 100 qubits, if you measure them all, that makes absolutely no sense. You know what I mean? Okay, TKM trained by VQA. Okay, so quantum support vector machine, I don't know if it avoids barren plateaus. It's being used a lot. It's a linear separation. It's a very simple technique, which puts most of the complexity into the preparation of the feature map. So the feature map gets trained, and yes, indeed, it avoids a lot of problems which other models have. But VQA, of course, is the process of training as opposed to the typical model. We could use quantum support vector machines for temporal quantum modeling as well.
Okay, thanks. Thank you, Jacob.
Okay.
I don't see more questions on the chat, so I recommend to move forward to the talk given by Sebastian. Sebastian will give a follow-up talk, so if there are some questions related to this talk, perhaps Sebastian could also answer, or Jacob will help. Good. Sebastian, I see that you are with us, so if you are ready, the Zoom is yours.
So at the beginning, again, thanks the organizers to invite me for this conference. I think that in the most case, it will be better called the quantum deep learning conference than quantum machine learning, but it's my opinion. And today I will, and I want to thank Jacob for his introduction to time. For physicists, time is very important because I am a physicist. And today I will try say something about quantum autoencoders. So this is just one specific type of quantum neural networks, but I will try do some tips how you can construct it and how you can use it for the noisy time series. So as we know, the time series analysis is well established. It's described by math, by stats, in economics, and many AI branches. And of course, there are many applications of that. We have just some value, and we checked how this value changed in the time. And sample application can be machine condition monitoring, astronomical observation. From business point of view, the most important is how to predict or forecast sales and other kinds of values in your business. And in the health, you can see EEG or ECG analysis. So this is typically a very famous kind of data. So it is good. As Paweł said, we try accept classical kinds of data to quantum computation. So here we have one of the most famous classical type of classical data. So our question is, okay, so can quantum machine learning assist in detecting some complex pattern in time series? And if yes, how we can use it? Okay, so from machine learning or from AI point of view, better say AI, I will try to define what I mean by autoencoders. We know that autoencoders are kinds of deep learning models, and these models try compress our data into some low-level space, and this compression should has essential features, or they should recover the original information from them. And but of course you can imagine these procedures as a PCA in the case of linear transformation, but autoencoders give you opportunity to give to process your data in not only on linear way. So traditional autoencoders are are neural networks with two neural networks. One is called encoder and the second one is called decoder. And you put your original input data to the encoder. You get this compressed representation of your data in a latent space. So you can put this, here you have some parameters, here you have also some parameters, and you can by decoder, you can reconstruct your data from compressed representation. So this is how typically autoencoders works. It's just nice to know that if you just use a linear transformation here and here, you get PCA methodology. But there is other kinds of autoencoders called denoising autoencoders, and this is just slight modification of our typical model that you can reduce noise from a real-world data set, but you take as input, you take noisy data and you try reconstruct clear version of your outputs. So the methodology is pure deep learning models. It is good to know that this is kinds of unsupervising modeling. So let's see how we can use it on the quantum level. On the quantum level, we propose with Jacob quantum autoencoders for time series data, and we checked if these kinds of models can have any potential to deal with high complex noise and anomaly patterns. These two elements are important for us because we want to reduce and reject the noise from our data, and because it is something bad for our prediction, and we want search something called anomaly patterns, and because anomaly is very important in any kinds of data, but of course it's case sensitive to define what's anomaly pattern, what's anomaly is. So training of these quantum autoencoders can be difficult because at the beginning we have potentially many features. So it could contain a lot of qubits and a lot of parameters. We have, as Jacob show us, we have complex measurement strategies. So we have many possibilities here to do this measurement, and this is unsupervised learning. So we don't have labels that tell us that something is noise or something is not noise, and possibly as Jacob show us possibly of barren plateau. So overall, we know on the quantum level we try use quantum neural networks terminology that we put encoder as a quantum circuit, decoder as also quantum circuit, independent. They are independent. So here in the middle we have some latent space and we trace space. And because this is a denoising quantum autoencoder type, we put input as an input. We put some noisy signal, and we try reconstruct our true time series sequence. As typically in the case of quantum neural network, we have some Q concepts include that we get model architecture, data encoding and decoding ansatz design, and of course parameters optimization strategy. So quickly, I will try say something about that. That in the case of the input encoding, because we have just a collection of real values, so this guided our selection of data encoding methods. So at the beginning, we of course choose one of them, but we try also in our experiments do every kinds of methods. But when in the case of basis encoding, so you just change your float number to its binary representation. And of course, it means that you need a lot of numbers of qubits. So we just reject these methods for our from our experiments. There is also a QRAM encoding where all possible inputs are known in advance. They are pre-coded in a circuit, and they can be used as a reference. But of course, in our approaching, we also reject this method. Amplitude encoding, what was question about, is one of the most useful encoding schemas from this point of view. But it enables us input as a circuit state normally. So you can input your data as some state on your qubits, and you measure them. As Jacob said, here is just example how it can looks like. But of course, the problem with this kinds of encoding schema is that for each unique input value, you have the structure of encoding gates is different. Yes, so because of that, we try use and of course the circuit is not differentiable, which may be suitable for simulators, but difficult to use with GPUs, and so you can have problems with time of computation. So we choose after checking this kinds of embeddings, we choose something called angel encodings, but in this typical way that we input value at qubit state rotation, but we because we try we can prepare our experimental data. We choose data that are scaled to -1 to 1. So in natural way, we can put our data by rotation from this x-axis. This x-axis is just plus state. So if we have a value beyond this 0, we can put them in this block, in this part of the block sphere by easy rotation. And after, if they are greater than 1, the points can be embedded somewhere here. So this is just one of the example how you can encode and embed your data for Hilbert space and states. And after of course there is problem also with measurement and interpretation. As Jacob said, we have possibility choose many ways how to measure the results, but everything is on the slide Jacob talking about. So I think that from our point of view, it is important that we choose just this one of these possibilities of measurement at the end. But maybe the main interesting thing is how we define our ansatz. So we try do this computation at the beginning on the QuizKit library. So as you can see, we have encoder as a parameterized circuit, and from the second side we have this nearly the same decoder. The same means, but that this is just ordinary picture that Paweł said about that each parameterized quantum circuit can contain parameterized gates and not parameterized gates. So typically that we have some rotation with parameters and entanglement blocks. So this is just if you can see, this is just mirror symmetry of this encoder. So in this case we try symmetric encoders and decoders, and because they are parameterized, we use a trainable rotation entangling layers and some entangling blocks. So of course there are many possibilities how to choose ansatz, but in our case we just try use this the simplest way. And of course the importance things is how we can change our parameters on how we can train our parameters. So the information is how we can learn our model to reconstruct our data. So we try different kinds of optimizer, but at the end we choose Cobula 1. So, but as one comments to the Jacob talk that I think that Jacob, what you mean at in the middle in the words that we should change to get better quantum models. We should change this automatically differentiation in the more and do this in the more quantum way than the classical way, because as I understand, the main problem is that in the classical level is this computation of the changes of the parameters. But this is just a short digression. And okay, so what we done? It was a few experiments. So this quantum autoencoders has ability to remove noise from signal and was comparable, but of course, as we suspect, not better as traditional deep learning model. This traditional deep learning model was made in PyTorch, and what we see is just we put training data here as this pure signal is as this blue line. We put some noise to them which is represented by this orange line, and our prediction get from our quantum autoencoders is described by this red line. So you see that it is not perfect, but it is very near the same as in the classical level. So this kinds of model can reconstruct this kinds of type of data. And because we use QuizKit, it was pure quantum autoencoders. So maybe one thing that this performance was good on the training data set, but of course in validation or test set, there was not so huge difference between a quantum version or classical version. So because we use Qiskit library, we have some problems with computation, time computation, and we maybe quickly, because I lose a lot of time because this technical issue. So we choose another approach for our development of quantum autoencoders, and we use Penny. So as Paweł said, Penny is just a nice way how we can put some classical layers for our neural network. So we can easy way we can construct and mixed classical layers with quantum layers. So we do something like that, and so in the case of Penny, you see that we have also this two blocks in many layers. So Penny it's a nice framework because it's cooperate very easy with PyTorch. So it has excellent support for gradient manipulation and providing several high efficiency gradient optimizers. So Qiskit, of course, also supports passing gradients into its optimizer, but it is not highlighted as a Qiskit feature. So in our work, this solution using PyTorch with Penny was also checked, and it was better way than just ordinary Qiskit. So here you can see that to go to the end of this presentation. So we saw on experiments that the larger the QA latent space, the better learning. So the latent space here you probably have. We try varying latent space. So the number of the qubits that you have in the latent space is different. So you see that more latent space, you have better solution and better model. So as we suspect for these kinds of data, and there is an optimal depth for the QA model, and with the limit of 1000 epochs, we can say that these kinds of quantum models outperform classical autoencoders. But of course, there was a question if the quantum models are faster or better. It depends, of course, how you define better and faster, because from business point of view, it's sometimes faster is not neglect that you don't need be faster because you have cloud environment, and you can if you need very high precision, you can do things slower but get more epochs, more computation, and better solution. So it's not that it's like in machine learning and AI that there is no free lunch. So it means that you shouldn't use one type of model for everything. So I think that because at this maybe short digression, that at this level of computation, there is just one main thing that you change your statistical point on the wages in the neural networks, and you change it to the gates, and the gates are more complicated. Of course, they are two-dimensional, and you can construct them to the more dimensional, but you have also some parameters of these elements. Of course, we know that we can use entanglement elements, etc., and there is hypercorrelation. But at this level, we can say that the quantum neural networks are really kinds of neural networks, but with some non-point elements. I think that this is how it should look like. So you see that we also try not only check if latent space is important, but also if circuit depth is circuit depth is important. And here you have comparison just classical deep learning model with quantum model. So you see that there is not so huge difference, but of course the most important is that what we get not only on the training set but also the validation set. So we can say that carefully that there is not so huge difference between these two, and at the end we try also different kinds of architectures that you cannot use this architecture. Someone asked about what is more than in quantum models than in classical models. Here you have a very nice example of what you can do more, because each gates are so each your circuits are reversible. You in the case of natural neural network, classical neural network, you don't have this possibility. So you can see here that you can choose. You can choose these properties and do something alternative from quantum models point of view. For example, you can put pure input data, and you can train decoder, and you can train the decoder. You can put somewhere here, and after that you can check if noisy encoder can be used. So here you first possibility is you have some trained weights, and you put everything here. You can construct, this important thing is here is Dagger, that you can construct your model as a how to say it, as a reverse quantum circuit. And the other possibility is very nice, that you can connect your decoder and encoder, but not on the level of each qubits, but only on the level of latent space, for example. So this is picture how you can use this encoder and this not classical parameterized circuit in other way than classical models. So I think I said everything at now. So thank you very much for your time and attention, and
Okay.
that is all.
Thank you. Thanks, Sebastian. Okay, we are running out of time, but let's see if there are some questions. Yes, there's a question from Arkit. In general, do QML researchers prefer to use Qiskit, Penelane plus PyTorch? What are the main differences, benefits of using it? So Sebastian, you mentioned about Penelane. Maybe you
Okay.
can.
Okay, so because maybe the best best person who can who can answer your question is Jacob, because he do a lot of this elements. But I think that I just take shortly information that we have problem with Qiskit in this new version. So this is the reason why we use Penelane. And in my opinion, Penelane is very nice connector with PyTorch. So if you just think about your quantum models as a quantum neural networks, and you won't learn quantum models as a neural network in classical way, it is very perfect environments, Penelane with PyTorch, that you can do this. So maybe Jacob, you can say something about that more.
From my point of view, Penelane with PyTorch is a very elegant framework. So we're talking about differentiable computing, and Penelane beautifully combines classical models with quantum models. So from that point of view, it is probably the best environment for putting together functions, matrices, classical programs and quantum programs. As long as all components are differentiable, they constitute a system. So it's a very beautiful architecture. Now, Qiskit is a great starting point for many people because it's a huge community of people. They have hackathons. Penelane also has hackathons, but Qiskit hackathon is 2,000 people. Penelane hackathon is 100. So it's a huge community. It's great for networking, and they have a lot of resources online. Why we abandoned Qiskit is that IBM decided to commercialize the product, and it's undergoing massive changes, very rapid changes, and open source community cannot catch up. So there's a lot of bugs in the software, like the quantum machine learning component has bugs because IBM is pushing development. So at this stage, it's worth waiting. I like both, but definitely Penelane is more stable and more robust, and it's a very beautiful architecture as well.
And because there is a question about Silk, I can just say that, okay, we know that Silk exists, but we cannot do everything and what type. In my opinion, it is good to choose one or two maximal framework to do computation, because you can do computation even in Julia, in other kinds of languages, but thinking and processing, putting gates, putting your circuit is nearly the same on these languages. So the difference is on the computational level. So yes, there is Circ, but in my I don't know if it is advanced than Penelane. We use Penelane, so this is my answer. And there is a nice question: the power of autoencoders as an unsupervised learning is on learning from a large data set. Yes, this is true, but it's very expensive in quantum computing. Yes, this is true, but you know, this is also a question for all kinds of quantum machine learnings, that if you have a lot of data by rows, it is okay. But if you have a lot of data with columns, you can use a classical methodology to reduce your data. You choose your most important features and do something like that. Yes, because even classical autoencoder can do this. So in my opinion, okay, this huge data are maybe not maybe we should devise two things, that there is quantum computation, that you use quantum computers to do new kinds of algorithms, and for huge amount of data it could be hard, but this quantum machine learning approach is different from that point of view, that you can do a lot of classical computation before you use your quantum machine learning model. Maybe this will be my answer. Sorry, Paweł, that I read the question and answer it.
Yes. Can I ask just one thing? For example, if you work in quantum chemistry, then you can't beat Qiskit. And the Qiskit libraries are fantastic for quantum chemistry. And they interface to existing databases, anything to do with physics. Qiskit has very well developed libraries for that, so you could actually do machine learning on chemical molecules and so on. You cannot do that easily with Penelane. Okay, so you would have to moving to third-party software for that. So if you in that field, Qiskit is probably the best tool you could have.
Okay, thanks. All right, I see some other messages. Commercials, yeah. So there was just a comment. I think that you've already answered all the questions. I'm not sure if this one was answered. What is hybrid latent space and why it has provided advantages? Sebastian, has you answered that one? I'm not sure if you want to answer actually, but you are muted now.
No, maybe I will try answer it by chat. Okay.
Okay, on chat. Okay, good. Thank you. All right. Yeah, indeed, we are slightly delayed, so let's go to the next talk, and the next speaker is Akash.
Yeah. So okay. So hi everyone. I'm going to talk about Kolmogorov-Arnold networks and how it can be used in quantum computing, mostly quantum computing, not like in any other quantum information or something, but it can be related in some way. But before going to the topic, I would like to thank Paweł for giving the invitation. I got his email like a few months ago, and I was really happy because I used to follow his conference last year as well. And one of my colleagues, Matthew, she also gave talk last year about quantum architecture search. So it was like really nice. Yeah, so a little bit about myself. My name is Akash Kundu, and I'm currently like a first year postdoc at University of Helsinki. And my topic is basically utilizing classical machine learning to understand and optimize quantum physics problems. And you can consider it as discovering quantum physics also using classical machine learning. So it's not kind of like quantum machine learning, but it's like I'm using classical machine learning with quantum physics to make quantum physics more like scalable in the sense of near-term devices. Yeah. So right now, so on this term, this thing came out last year, Kolmogorov-Arnold network, and it is like very interesting development in classical machine learning field. And this was an open question that how this neural network, which is the replacement of neural network, like multineural perceptrons, can be used in quantum computing in the first place. So yeah, so this is the basically the outline of my talk. I'm going to introduce KANQAS, which are Kolmogorov-Arnold network. Then I'm going to introduce something called quantum architecture search and how KANQAS can be used for quantum architecture search methods, some results, and eventually some summary, and also future works, which is basically open for collaboration kind of stuff. So at first, I'm going to refer to the main paper, which is KANQAS, and this is by far one of the best paper I've read, not in terms of only contribution, but also in terms of like text itself and how the authors actually put the story about multilayer perceptrons and KANQAS. And I have been in close contact with Ziming Liu as well, so it was like really interesting. And recently, it has been published in ICLR 2025. So in the abstract, if you go through the paper, which is the accepted version of the paper, you will see that they're basically introducing the Kolmogorov-Arnold networks as the alternatives for MLP, specifically when the interpretability of the like learning process is desired. We're going to talk about that eventually, but let us just highlight the main points of KANQAS first. And second, that they're saying that KANQAS are more interesting because in the MLPs, you have these fixed activation functions, which are ReLU, leaky ReLU, or like the other activation functions. But in KANQAS, you don't have specific activation functions, but you can learn them. So KANQAS is actually, in KANQAS, the weights of the activation functions are actually learnable in this case. So that's very different. And at the same time, KANQAS are shown to be more accurate and have faster scaling laws than MLPs, specifically in function fitting and PDE, which is also a very specific example. But even though all this is fine, but it has been shown that KANQAS are a little bit slower than MLPs when you are training for a long time. So we'll talk about all these specific topics in terms of quantum computing as well, and how these classical insights can be translated into quantum, and can we face these problems in quantum domain as well. But before that, let us talk about a KANQAS a little bit, but probably majority of you heard about this because this has been like quite a viral paper. That this KANQAS actually comes from the CART, which is the Kolmogorov-Arnold representation theorem. And this theorem actually says that every multivariate continuous function can be represented as a composition of continuous univariate functions and the binary operation of addition. So let us decompose this statement, compact statement, a little bit. So a multivariate function can be represented by f, which is depending on multiple variables like x1, x2 to xn. And as per Kolmogorov-Arnold theorem, we can represent this multivariate function in terms of univariate functions, which are basically functions that are depending on one variable from these multivariate functions. Like phi1 is an univariate function depending on x1, so on, and phi n is depending on xn. So if we take a binary operation of addition of these univariate functions, then we get a multivariate function. Then we literally get a multivariate function. And then what we basically do is that if we sum is up, then we create a single composition of this multivariate function, where this composition is basically an univariate function. So this phi is here and is an univariate function, and we take a composition of this sum of all this multivariate function. And this is just one composition, because there can be many different compositions, or which basically means is that different representation of this univariate function can have to create a composition. So we take basically 2n plus 1 different compositions, and according to Kolmogorov-Arnold representation theorem, if you take n enough compositions of this sum of univariate functions, you get back to this multivariate function. So basically you don't have to so basically the consequence is that you don't have to calculate the multivariate function itself, but you can take univariate functions, sum them up, and put them inside an univariate function, take multiple compositions, so you get the multivariate function itself. Now, how this theorem can be seen as a Kolmogorov-Arnold network, right? So for an example, if we take this equation on the right hand side, then we can represent it as an inside layer, which is the sum of univariate functions, and then outer layer, which is the multiple compositions of these univariate functions, right? So if we take the inner function, then we have n output, which is basically univariate functions. Then we get 2n plus 1 outputs, which are basically different compositions. And then if we take 2n plus 1 inputs for the output composition, then we get just one output, which is basically the multivariate function. And then in this case, we can consider this phi, which are basically multiple univariate function, which are summing up as an individual univariate functions in a matrix formalism. And this phi 1 goes to 2n plus 1 to n. So 2n plus 1 is basically the number of compositions, and n is basically the number of univariate functions, which are applying in something called like an n number of features, input features. And in Kant paper, the authors actually consider this each and every individual functions as a learnable parameter of a polynomial function, x squared plus bx plus c. And then if you consider that, then what you basically get is that, for an example, consider you have right now not n unit input features, but just 2 input features. Then you can process it through 5 different compositions of univariate functions, basically phi 11, phi 12 to phi 15. And then you can consider the x2 another set of univariate function, which is 5 univariate functions, and then you just sum them up. So phi 11, phi 21, then phi 12, phi 22, phi 13, phi 23, and so on and so forth, and you get the output for your whole function to create the multivariate function. So when you implement in a neural network formalism, this function creates one Kern layer, and you can stack them up over and over again, and you can learn basically this A, B, and C of these activation functions, which are basically these univariate functions. And eventually you can learn this x1 and x2 functions itself as an output, this distribution. So this is basically one Kern layer. Now, what is the important thing about this Kern? Because this sounds very sophisticated, but how can it be used? And how can you use this back propagation in this case? Because as you remember, this A and B and C are continuous parameters, but we need like some differential parameters to be fitted as an MLP or like, as a neural network formalism, right? So in MLP, you have basically these 4 widely used activation functions. People right now use Licky-ReLU because of its efficiency. But in Kern, we have basically this phi 11, phi 12, and different activation functions. Now let us consider we take just only one activation functions, but you have to remember that it is very non-trivial to make it well optimized for a specific input. But then what we do basically is that the authors in the paper itself considered something called a residual activation function. So what they do basically is that they took these 5 functions, they decompose into 2 different like functions, bx and spline of x. Let us I'm not going to go deeper into the b of x. It is basically a basis function which like a modified version of this sigmoid function, but it's called a silu x function. But and it also has an weight omega b. But let us talk about this spline x. What is this spline x? This spline x is basically a linear combination of b splines, and this b spline depend on different weights of the parameter. Now this b splines basically does something very interesting, which makes the function creates into a discrete set of intervals, so that you can use back propagation when you implement it in, for an example, in TensorFlow. So because of this b spline, you can decompose this polynomial into lower order polynomials. Basically, if you have this function, you can create some local control points such as b1, b3, b5, b7. Then you can connect the some points on that polynomial through these local controls. So what basically happens is that you don't have to control b0, b2, but you're controlling b0, b2 through b0, b1 and b1, b2. Now, what is the advantage of using this? The advantage is basically b splines, basically this decomposed part gives you local controls. Now, what is the local control? Then if you have this red curve instead of this continuous polynomial curve, then what basically happens is that if you change this curve, then it just made modification on this specific part. So that basically means is that, consider if you have already trained KAN, then you are trying to fit that particular trained KAN into some other problem. Then what happens is that you don't need to train the whole KAN model. You basically need to train some part of it, like some local control of it. And that is why it is much easier that if you train KAN on something else, then you train KAN on some related problem to that, then you don't have to train the new KAN as much you train the previous KAN for the previous problem, because you just have to change the local controls of it, and it might fit the new data set. And at the same time, you can fine tune the KANs with more grids. More grids basically means is that you are enabling more local controls. Such, for an example, you are decomposing B0, B1 into maybe B0, 1, B1, 2 or something like that, like more continuous points. So basically it happens is that it indeed increases the number of parameters in training, but it makes the training more efficient to the data. Now, okay, now directly we're going to jump to quantum part, because this is the introduction to the KAN, and how it can be used in quantum part can be only possible if I explain properly the quantum part itself, right? So last year, my colleague Mateusz, who I cited in the beginning, he came and talked about quantum architecture search. You can actually find out the talk if you go to the website, basically the YouTube of Quantum AI Foundation and these talks, right? But I'm going to give a very small introduction. So this is basically a copy of the paper, basically the KANQAS paper, which we published recently. In the paper, we basically says is that this quantum architecture search is basically a problem where we automate the optimization of quantum circuit, the search of quantum circuit by some search method. It can be like a classical machine learning method. It can be simulated annealing. It can be a quantum method as well, like quantum assisted quantum method as well. But here we are going to mostly focus on classical machine learning method. And it has been inspired by neural architecture search. You can see there is a name like quantum architecture search and neural architecture search. So QoS is divided basically into 2 parts. In the first part, there is a template of the circuit you have, which is basically a parameterized quantum circuit, which consists of rotation gates, and you optimize these gates using a classical optimizer. And the classical optimizer feedbacks the angle to the parameterized gates, and then it tries to optimize some specific problem using this loop, like quantum circuit, classical optimizer, and then it sees that, okay, if this parameter, the classical optimizer decides if this parameter is actually suitable to give me some suitable outcome for a problem. So this is basically called a variational quantum algorithm loop. And in the next part, what basically happens is that instead of we are deciding that if it is a good optimization of these parameters of the network of the quantum circuit is not, we let it decide by a search algorithm. In this case, we are going to use reinforcement learning, obviously, for that. There are many reasons why you use reinforcement learning. One of the thing is basically that reinforcement learning does not require any specific like expert knowledge of the domain. You just construct a suitable reward function for your problem, and then you can optimize it. Like, let me explain properly to you what I mean by that. So in the reinforcement learning for quantum architecture search, what you basically do is that the quantum circuit is defined as a sequence of actions generated by a trainable policy, and the cost function's value serves as a signal for the reward function. So you basically says is that, for an example, consider you're solving like a VQE problem, and your cost function is basically the expectation value of the Hamiltonian, and you just say that, okay, if the expectation value is close to my ground state, please give me like a positive 5 outcome, and if not, please give me a negative 5 outcome, right? I mean, it is like as simple as that. It can be, but our reward function is a little bit complicated, but I'm just giving you an example, right? So what you do basically is that you feed the reward function to the policy, and what the policy is basically is that it has this state, which is basically the binary representation of this quantum computer, basically the parametric quantum circuit, and we feed it to the DDQN network as an RL state, and at the same time we feed some reward, basically the +5, -5, or plus integer, minus integer value to the agent, depending on the RL state and the reward function. The DDQN network has access to a set of actions that can be applied to the quantum circuit, and what it does is that it just projects the state into, it just applies all the actions to the input state, and it creates a probability distribution, which is basically Markov decision process, and it assigns the highest weight to that action, which is taking the cost function closest to the ground state energy. So this policy can be as simple as that. In our case, we are not using any policy, we're using value function because it's a double deep Q network, which is off policy learning. And eventually this RL state is actually decomposed, like expressed into 3-dimensional tensor. So in X dimension, you have this number of qubits of the circuit. In Y dimension, you have this which kind of gate can be applied. In Z dimension, you have basically how many depth. And if some of you people don't know what is a depth is basically how many operations in a quantum computer can you do in parallel. So basically, if you see in the circuit here, Rx, the C0 between 1 and 2, the RY and RZ can be actually done in parallel in quantum computer. So that's why this one depth can be made in just one chunk of this tensor. So we have this 3-dimensional parameter, which is basically depth, then we have this remaining part, number of gates and type. So what we have is basically that we encode the 1 and 2 qubit gates in the first and the second part. Now, how KAN can be introduced in this architecture? So what we basically do is that we have this RL structure, which is basically operating on double deep Q network. We basically replace the MLP with KAN. But replacing MLP with KAN is not that simple because the KANs have specifically this grid structure and number of splines. So you have to, so for a fair comparison, you have to take care that if the MLP has actually the similar number of parameters in the multi-layer perceptron structure as a KAN in the KANQAS structure. So the whole structure right now looks like this. So we replace this double deep Q network with Kolmogorov-Arnold Q network. We just name it like that. I mean, we didn't name it. There's a GitHub repository which actually attempted it. We use that repository as well for us, for our research. So yeah, so to benchmark, so to achieve a comparison of better performance, so our main aim is to see if KANs instead of MLP can actually achieve better performance and comparable performance while mitigating the issue of parameter growth in parametric quantum circuit or in MLP networks. Because previous works we have seen that, for an example, if you want to find the ground state of a 6-qubit molecule, you need, for an example, 1000 new networks, right? But if you go for 8-qubit network, you need the number like at least twice as much. So the number of neurons and the depth of the neural network of MLP increases like linearly, which sounds good, but the number of parameters increases much faster than that, because you are not only increasing the number of neurons, but also the number of layers and neurons as well. So our main aim is to see if the parameter growth can be reduced with KAN, and at the same time, can we actually overcome the activation function selection. So for that, we tackle two problems. One is quantum state preparation. So we basically prepare 2-qubit maximally and 3-qubit maximally entangled states, which is a state-of-the-art problem for classical machine learning with quantum architecture search. And we consider small molecules for quantum chemistry problems like 4-qubit lithium hydride and 4-qubit H2 problem. So eventually what we basically do is that in quantum chemistry, the main aim is basically to find the chemical accuracy, which is 1.6 × 10⁻³ in this case. So we just try to answer these 4 questions. One is that does KAN gives a better success rate than MLP with increasing training time? Does KAN utilize less number of trainable parameters than MLP, or is KAN better than MLP in optimizing the structure of parametric circuit, which will be basically for quantum chemistry problem? And is KAN is more interpretable, which is the promise of the paper as well, right? The KAN paper. So what we saw basically is that does KAN have a success rate? So here success rate basically means is that finding a circuit that construct the quantum state, that prepares the quantum state with a predefined precision. In our case, the precision was basically like 98, like 0.98 fidelity, very close to 1. Anything above that is a success, you can say, in an episode. And for your information, we used actually 10,000 episodes, and each episode is divided into multiple steps. Here is basically 6. So you can say like we run it for 60,000 epochs. And here the interval is basically that if you go up, that each interval contains a specific number of episodes. So basically is that if there are 4 intervals, and if we have 10,000 episodes, so we divide it into 4 intervals, basically means is that each interval contains 2,500 episodes. So for 2-qubit QSP, you can see that KAN and MLP almost performs equally. There is no difference in terms of probability of success and finding the optimal circuit, which is basically Hadamard C0 and in this case, right? There is no difference. But then when you increase the number of qubit to 3-qubit, finding the GHZ state, we see that KAN actually gives much higher success rate as the number of intervals, basically the number of episode increases. And at the same time, KAN is able to reproduce the optimal structure of the circuit, basically the Hadamard C0 and C0, this GHZ structure, much more frequently than KAN, which basically means is that KAN actually have, because we use DDQN, the algorithm is not different, KAN actually has a better structure to not forget, you can say, the optimal solutions, or it is more reliable when you are using it for an example, for long time learning in this case, which you show for QSP problem. So the answer is basically yes. And the second thing is that does KAN utilize less number of parameters? We see actually yes. For Bell state preparation, we see like almost 4 times less parameters. For GHZ state, it's like 2 times, not that much. But for Bell state preparation in a noisy scenario, we used like depolarizing noise, not like very complicated, because we wanted to keep it very simple. The number of parameters is also like 3 times higher. But when observing the Bell state preparation in noisy scenario, we saw something very, very interesting. And we're going to talk about an activation function a little bit more here. That in the Bell state preparation, as you can see that KAN, MLP, and we have 2 structures of MLP, that KAN actually having that 0.732 weight, which is much better than different structures, like different activation functions with the same MLP. So basically, even if we are varying the activation functions for a different, for a specific MLP of a specific size, we cannot achieve a comparable or better fidelity than KAN with a very small size, right? But then even if you increase the MLP size to 4 basically means 4 layers and 100 is basically the number of neurons. So you see that with ELU and ReLU, we cannot achieve equal fidelity as KAN. But at the same time, when we use leaky ReLU, we actually beat KAN much higher. So our main point about is that it's not like we're trying to claim that KAN is much better than MLP, but we're trying to focus on the fact that KAN outperforms MLP, but MLP outperforms KAN, but it requires a very fine choice of number of layers, number of neurons per layer, and the activation function itself. Because generically, like in generic research, people usually use ReLU and 4 layers is deep enough for a 3-qubit problem, like 2-qubit problem, right? And 100 neurons is enough for this problem. But we see that it cannot achieve for KAN. But if you have like enough, like it basically indicates the fact that you have to probably use some kind of neural architecture search on quantum architecture search to find like a suitable parameter choice to beat KAN with MLP. But KAN can indeed, MLP can indeed beat KAN if you have deep enough and proper enough activation function. The third is that is KAN better than MLP in optimizing circuit structure for PQCs? We found out that for H2 quantum chemistry problem, we actually have, as you can see, that we have 2-qubit gates depth and number of gates. The average is basically, you have to remember that the average is taken over different initialization of the neural network. So for MLP, it is basically that we initialize the MLP for 20 different times for different random weights of the neural network. And for KAN is basically the different weights of the splines and the basis function in this case. So 20 different times. So we're taking average of that. So as you can see that KAN is actually consistently giving you less number of 2-qubit gates, which is supposed to be more costly in a noisy scenario, but the minimum number of gates is same. So if you're trying to consider that, okay, please give me the best initialization of the neural network for both of them, then KAN and MLP works equally. But if you choose the average performance, KAN is much better. But at the same time, if you are concerned about the depth of the circuit, always go for MLP in average, but KAN and MLP more or less similar. And at the same time, if you're trying to minimize the number of 1-qubit gate, which is basically the parameterized gates, I would prefer you to choose MLP than KAN. So KAN is giving you advantage for H2, like finding the ground state of H2 in terms of only 2-qubit gate. And at the same time, if you go for lithium hydride, we see something very interesting that if we go for harder problem, which is supposed to be a little bit harder, right? Harder problem, lithium hydride, which is more like correlated than H2, we actually basically see that KAN is actually giving us much less deeper circuit and less 2-qubit gates in average and in minimum than MLP with higher number of parameters. So in the box, I didn't say to you that in the box, which are these numbers is basically is a number of trainable parameters in MLP and KAN. But once again, if you want to optimize the number of 1-qubit gates, which is the parameterized gates in a circuit, parametric quantum circuit, indeed go for MLP, not KAN. So yeah, in some cases, KAN actually can give you much better circuit than MLP for the same problem. Now, is KAN more interpretable? Which in the paper we did not actually talk about too much, but if you go to the GitHub, you can find this very weirdly looking plot, which is basically for 2-qubit maximally entangled state preparation. So this is basically the one training loop of KAN and finding the solution. So you can see that initially we have this tensor encoded the 3D dimensional circuit encoding and input as a KAN. But as you can see, this is very important that some neurons are more activated than other. So if you see that a neuron is deeper, like a line is deeper, which is basically more impacting on the outcome of this optimal structure than the other. So it basically indicates is that if you're training KAN and if you're using it for retraining, you can actually reduce or like to be more specific, you can remove these nodes, these layers or these activation functions, which are not actually that contributing to the final outcome. Like for an example, if you go in the top, you see that third one is not actually impacting that much. So even if you decrease that, like remove that from while doing the retraining for this 2-qubit case, you will indeed get good enough outcome. But yes, so that is why we did not research that yet in the paper, because the paper was already quite long. So we just said that it needs more research. So how slower is KAN than MLP? This is a very important thing, because I told all the good things about KAN and MLP. So it is not like always rainbows and fairy tales, but KAN is actually bad in terms of average time per episode. And these times are actually in second. So average time per episode, it takes like 4 to 5 times, sometimes even 10 times. Like even if you go the new versions of KAN, which is basically efficient KAN, which are supposed to be the fastest version of KANs, they even take like in some cases 10 times slower time in training the same network as MLP, as KANs, like as MLPs, right? So if you're considering training it for a long time, you might probably get less number of training episodes with KAN for a specific computation budget than MLP. So yeah, so you have to manufacture the KAN's configuration files or hyperparameters as per this time limit. So, okay, let me summarize the talk right now, because I'm almost at the end. That we saw that in the KAN part, that there is this Kolmogorov-Arnold representation theorem leads to Kolmogorov-Arnold networks, and in KAN's the activation functions represented by these B-splines, which are very beautiful structure, and you can train these B-splines corresponding to the weights of the B-splines, and it makes this trainable, so you don't have to choose a specific activation function. Some splines become finer as the grid size increases, and the number of trainable parameters are less in KAN than MLP, but you see that the KAN is actually slower than MLP, so there is a trade-off between that. And KAN has local controls, so it makes more suitable for continual learning. And we did not talk about this in the paper itself. I mean, I think we talked about this in the paper, like some future work, but not in the conclusion, because we did not work on that. But I think this is a very interesting part as well. So in summary, for KANQAS, that we have this quantum architecture search that deal with the automatic search of optimal quantum circuit structure for variational quantum algorithms for a specific task. QoS is widely used under the reinforcement learning framework. And in the reinforcement learning framework for KANQAS, we replace this MLPs with KANs for QoS problem. KANs give a higher success rate finding the optimal circuit than MLPs. KAN require much less trainable parameters, sometimes even like 100 times less than MLPs. And KAN in some cases provide more compact circuit in terms of 2-qubit gates and depth for some problems than MLPs in quantum chemistry problems. Now let me talk about a little bit future work. So in the case of future work, I would like to see personally that more towards an explainable and interpretable QoS with KAN, because I showed you this plot. Probably it will be very interesting. For an example, consider like I give you like a network structure like that, and I tell you that which problem I'm training. Then you can tell me that, okay, I mean, you can optimize the structure again, then you can retrain the problem with much less resources using that particular image, which says that, okay, some nodes are activated or not. So this might be very interesting for a future work. And the second, which we did not talk about at all in the paper, like in terms of experiments, that utilizing the local control feature of KANs for continual learning. So for an example, if you are training a very easy quantum problems, like quantum chemistry problem, for an example, then you take the same KAN and teach it for harder quantum problem, then probably it might be easier to train it in the harder problem, because there are local controls and you can change it locally. Towards explainable interpretability of KANs, I mean, it is not related to KAN, but it is related to most MLP. But in one of the recent, in my work, actually, we showed that we can use something called a program synthesis. Like basically, if you have like a problem, basically we consider this traverse field Ising model. So if you vary this magnetic field strength towards 1, which is basically phase change point, the normal reinforcement learning algorithm in this particular action space of CZRZ SXX, which is basically Qiskit's framework, like real device framework, it cannot actually find a very good approximation. It gets stuck above 10 to the power minus 3 like error. But at the same time, if you take this bad solution, for an example, it can give you good solution with above how to say, above phase change point. So you can take those problems which are supposed to be easy problems, and you can run through program synthesis method. So it can find some repeating structure of the quantum circuit, because the RL actually learning this problem, easy problem, and you can find out some circuit structure that are repeating, and you can use these structures in the addition of this action space. So which is basically we call a gadget, which is found by this program synthesis, and you can actually interpret the action space from these learned problems to solve the hard problems in more efficiently. So as you can see, this green line before with RL was like above 10 to the power -3, but after GRL, which is basically gadget reinforcement learning, we go beyond like machine precision. So this is one of the ways you can actually use this interpretable or explainable like QAs for RL. So yeah, this is my whole talk. I hope some of you find it interesting and would like to work on this direction or go through it, but I'm open for questions kindly. Yeah, please. Thank you.
Okay, great. Thank you, Akash. All right, we actually already have a few questions on the chat, so I will start from the question from Sebastian. Are CAN networks just a specific choice of basis for function representation, and can they be compared to the Fourier decomposition?
Yeah, I mean, this is a very interesting question. Like recently, paper came out that they consider this Fourier structure for like basis functions. So indeed, yeah, it can be considered, and the basis function can be considered as the suitable because they consider specifically this SILU one, but you can actually consider like any structure that can be suitable for the problem. So Sebastian is right,
Okay,
actually.
good.
Yeah.
All right, there's another question from Sebastian. Is spline a piecewise linearization of a function?
I would not say linearization, but it's still quadratic, like or some like lower order polynomial than the whole problem. But it is, I mean, if you say linearization is basically like summation of lower order polynomials, then you are right. But it is not making the function linear itself. It is kind of quadratic in sense, yeah.
Okay. There's another question from Arkit. In the ansatz evaluation by cost function calculation done on a batch-wise basis or a stochastic basis. Stochastic is training example-wise. And there is another question, but maybe you can first answer this one.
I mean, I actually did not understand because you're talking about this parameters of the neural like circuit, right?
Arkit, maybe you can unmute yourself and clarify.
Yeah.
If you are still with us.
Yes, so you said the reward function is passes a feedback signal to the RL. So when you're doing this evaluation of the cost function, is it with respect to one training example in a stochastic manner, or are you training like one specific ansatz completely? And
This is
then
a very interesting question. I mean, I'd like this question, but in our case, I did not go through the example like very like detailed, but basically we're starting from an empty circuit, okay? So after the RL agent actually suggesting one gate for an example, we are evaluating the reward. Then the next gate corresponding to that reward actually decided by the RL once again. So we are not actually, I mean, you can actually do that. Okay, let the RL add 10 gates or 5 gates or n number of gates, then we evaluate the reward, right? This is also possible. But we are actually doing more local training than global. So you can actually train it in batch, the reward function, but at the same time, we are training in this case more locally, like after each and every operation.
okay, that answers my question. Thank you.
Yeah, thank you. Yeah.
Okay, good, thanks. There are two more questions, or even more. Another is from Ravi. Where have you simulated those results? The question is about the platform.
Yeah, I mean, I also wanted to talk about that. The quantum part has been done in, like, I think it was in Qiskit. Yeah, it was in Qiskit actually. But I mean, I forgot because I mostly use QLAX, but yeah, but I use it for bigger problems, but it was in Qiskit, I think. You can check the GitHub.
Okay.
I did not put the link. I'm sorry. Yeah.
That's fine. Another question. In the machine learning sense, do you think KAN does not need nonlinearity to solve the XOR problem?
Does not what? Can you please repeat?
Does not need nonlinearity to solve the XOR problem. XOR. You
I
can
think this
find
is
the question on the.
actually, yeah, I mean, I think I have to check it, but I think I'm understanding a little bit. Probably it is the case, but I will just check it. Yeah, I'm not sure.
I can
Okay.
explain my question if you want.
Yeah,
Yes, please.
So in general, in machine learning sense, when we solve MLP through MLP and XOR problem, we need a hidden layer, which essentially provide nonlinearity. Then we are able to solve the XOR problem. So in the sense of benefit through KN, I was thinking that whether do we need the similar structure or not, which essentially providing nonlinearity. Thank you.
Actually, I mean, thanks for saying the question, because right now I understand you indeed need the nonlinearity, but you can actually train how much nonlinearity you need. So for an example, in MLP, you probably overshooting the nonlinearity, right? By some activation function, but in KAN, you can just train it. So how much nonlinearity you can need. So probably it will be much different than MLP. And you might not
Maybe
need.
I need to, maybe I need to do it and then see how it goes. Yeah.
Exactly.
Thank you very much,
I mean, go ahead, please. Yeah, that
Yeah.
will be amazing.
Okay, good. And there is another question. My question is due to limits of classic computer for computing. How either KAN or MLP could try to optimize quantum computer for even larger computing tasks? Are you trying to
Very good
justify you
question.
can use? Yeah. Are you
Very
trying
good
to
question.
justify you can use classic computer to optimize quantum computer both for computing purpose? I consider you run KAN or MLP on classical computer or not. So
With
this is the
KAN,
last question.
yeah, with KAN, the scalability is a problem. With MLP, actually, for higher, you can actually go, for now, you can actually go up to like 10 qubits. But, like, okay, so the most important problem is that I would like to say the problem itself before giving you a number of qubits, right? That after, like, when you're interacting with the environment, with the agent, then you have these episodes, right? So each and every episode is basically decomposed into consider 10 number of steps, and each step you add one gate, right? So you have to evaluate the quantum circuit or the quantum simulator, or call it equal amount of time each episode as the number of steps. So when you increase the number of qubits, then you have to call the simulator for that particular qubit multiple times, right? For one episode. So it takes really costly, and the bottleneck is not the classical machine learning, but it's mostly the unoptimized version of quantum simulators at this moment. Probably the GPU can help for this, but we can. I never used CUDA quantum for that. So, but Qiskit is quite inefficient if you go beyond 10 qubits. Yeah. So the bottleneck is not the classical machine learning, but it's the quantum simulators at this moment.
So can
Yeah.
I understand that for current moment, the quantum computer is still under the simulated control or optimization schemes of the classical computers, but it has blueprinted out for larger vision task already. Is it correct or not?
I could not understand. Sorry.
So
Could you please repeat?
If you have my same question, my question is the same as I stated in the chat box. So you are using classical computers, the computing capacities, to optimize the future quantum computer. And would there just be a bottleneck, or just?
I
think that the
it
question
will
on the chat was, yes, please go on.
No, I mean, yeah, it is in the chat, so I will just stop sharing and see the chat actually, because that will be much simpler for me.
We can share it direct.
Yeah, the question is, can you use classical computer to optimize quantum computer both for computing purpose?
I think yes, this is possible. I mean, with KAN, I'm not sure. More research need to be done, but with MLP, definitely. I mean, yeah. I mean, if you can promise me that, okay, the quantum computers are in a good condition right now, like, and it's fast enough. So yeah, it's possible. There is no bottleneck from the classical machine learning part. So it's possible actually.
Okay.
Yeah.
All right. We need to go to the next talk. So if there are any more questions to Akash, I'm not sure, Akash, if you will stay with us. I hope so. Then please post the questions on the chat, and Akash can try to answer on the chat.
Yeah, definitely.
And
Thanks.
now yes, I would like to invite. So thank you once again, Akash, for the great talk.
Yeah, thank you
It
for
was
the
very
talk.
interesting and very interesting discussion. And I would like to invite the next speaker, Artur Miroszewski. So Artur, if you are ready, you can start sharing your screen.
Using Central European time, good afternoon, everybody. My name is Artur Miroszewski. I'm a postdoctoral researcher at the Jagiellonian University in Kraków, Poland. I'm a part of the Quantum Cosmos. Can you see my mouse also?
Yes, yes.
Okay, that's great. I'm a part of a Quantum Cosmos lab group at the Jagiellonian University, and quite recently, together with Gabriele Cavallaro and Upendra Singh, we've created a new technical committee, Quest technical committee within the structures of IEEE Geoscience and Remote Sensing Society. And this technical committee is devoted to using quantum computation. There are two work groups, using quantum computation, or there's the first group, and the second one is quantum sensing for Earth observation. And as you can already see, I've been involved in using quantum computing for problems related to Earth observations. And in fact, for the last 3 years, I've been conducting research in the project called Quantum Machine Learning for Analyzing Multi- and Hyperspectral Satellite Images that was founded by European Space Agency, and that work was done in the collaboration between Jagiellonian University, private company KP Labs from a space sector, and a part of European Space Agency, which is called ESA PhilLab. Yeah, so within this work, we've focused on many things, and actually the project finished last November, and for a final milestone, we've prepared quite a nice report, I would say. I hope that's available if you're interested via this QR code. It's over 100 pages on the topics listed on the left. And actually today I thought that maybe I will just address one of those issues, which can be seen as an elephant in the room that's overlooked in many cases. And this elephant in the room will be actually connected to, as I know, any quantum machine learning problems, but as I've been working with quantum kernel methods, then I will focus on quantum kernel methods. So just to set the stage for the presentation, well, there are many ways to divide or classify quantum machine learning into, well, different groups. But from my perspective for the talk, I would like to divide quantum machine learning, the part devoted for a near-term devices, or maybe algorithms which were designed keeping in mind the near-term quantum devices, and also the long-term. The second group is a long-term quantum devices that have error-corrected error correcting codes implemented. And finally, those kind of algorithms were developed earlier than the near-term devices, near-term algorithm. And within the group of near-term algorithm, we can distinguish, well, different groups. I would say that the most known is the quantum neural networks or parameterized quantum circuits, let's say. But The second big group is quantum kernel methods that I will focus on today. In many cases, those two approaches are completely equivalent, but as I believe the theory of kernel methods is, well, inherited from, for quantum kernel methods, is inherited from classical machine learning, and it's very well developed for classical algorithms. So we have quite a nice toolbox to look at quantum machine learning from the point of view of kernel methods. And for most of my time, I've been using quantum kernel SVMs that I will explain on the next slide. So just a word of caution that I will mostly relate to quantum kernel SVMs, but the things I will mention today are universal for basically any quantum kernel method, and they easily translate to neural networks. Okay, so I'm sorry if I'm right now introducing some redundancy, but I was only able to join already after 12. So if all those things were mentioned before, then, well, you'll have to listen again to that. And so what is classical support vector machines algorithm? So it's a supervised classification algorithm. And in the simplest case, the setup is that we have a data set with points labeled with two types of labels. And what we would like to do is to separate points labeled with one label from the other, from the points labeled with the other label. And we separate it by using, by finding a hyperplane that divides those different two types of points. There are infinitely many on this picture hyperplanes that can separate those points, but in the support vector machines, what we aim for is to maximize the margin between, or the distance between the hyperplane to perpendicular distance in this case to the closest points from different classes. Okay, and well, maximizing margins is believed to increase the generalization of this algorithm, and in many cases it's an extremely powerful classic machine learning algorithm, but actually its power is even uplifted when we realize that it can be formulated slightly differently than given here. It's called a dual formulation. Its optimization problem is completely equivalent to the primal primary formulation, but it's translated in such a way that it depends on data only through inner products between pairs of points. Okay, and that's actually a great thing because it allows us to calculate those inner products in not maybe in the initial space of features that we have, but well, it allows us to first transform the features into some other space, perform some kind of transformation, phi transformation, and then calculate the inner product. Why is it important? Well, because in many cases we can use a transformation that embeds the data into higher dimensional space, and in this case the separability that, well, here was quite obvious, and for many data sets it's not obvious. In higher dimensions, well, is increased, as you can see here, going from 2 dimension to 3 dimension. And the second thing that that underlines the power of this using this transformation and the inner product, which is called, by the way, kernel trick, is that, well, if we separate the classes into in the higher dimensional space, go back to the original feature space, we get nonlinear. We can get nonlinear class boundaries. So it's not only hyperplane that we are using, but, well, the projection on of the hyperplane, which can be nonlinear well, in this lower dimensional or the initial feature spaces. And what we actually use in the algorithm is so-called the kernel matrix that we create in the way that I mentioned before. And this can serve as an input for an optimization routine of a support vector machine. So the natural idea of quantum kernel methods was to calculate the kernel matrix on a quantum computer and have it as an input matrix for a classical machine learning routine, which is very well optimized and, well, in many cases, at least in the near-term devices, we will not be able to go faster with this optimization. So we just use, we take some data. It could be classical or quantum. I'll stick with classical data. Perform quantum kernel estimation, so obtain the quantum kernel matrix, and then use a classical routine. So what I would like to talk about, what I would like to focus on today is the quantum kernel estimation. Usually, well, it consists, if we have classical data, we have to embed them, embed the data into some quantum state, perform some computation, perform some gates, perform repeated measurements, and possible post-processing. And in this way, we obtain the kernel matrix. Why we believed at start that it's a good idea to use a quantum computer for quantum kernel estimation? Well, so the first observation is that using n-qubit quantum computer, we theoretically have access to exponentially big target spaces. So we embed data in the 2 to the n dimensional Hilbert space. Additionally, there are families of functions that can be performed, can be calculated on a quantum computer with polynomial number of gates, while they are proven to be exponentially hard to calculate on the classical computer. So that's a natural families of functions that would like to look into when encoding quantum kernel estimation. In most cases, those functions utilize highly entangled states, and that's another initial belief that in highly entangled systems, we will be able to find new patterns in the data. In other words, I would say that, well, with functions that are infeasible to perform, to calculate classically, well, they are not explored if they are useful for classification. Well, because they were infeasible to calculate, right? So no one looked at them. But with a quantum computers, we somehow extend that set of functions or set of transformations that we use for quantum kernels. And when do we believe that it would be useful to use quantum kernels? Well, so the first point is, well, we would like to get better machine learning performance. If we don't get better machine learning performance, then in general, we'll opt with classical, the fully classical routine. But that's actually lots of work in the field is devoted to assessing how good machine learning performance can be with those quantum machine learning methods. And that's something I'll not talk about today, but I'm more interested in whether we can actually be faster, like really faster with those computations as we initially believed when performing quantum kernel estimation. Okay, and yeah, that's something I would like to focus on today. I would like to quickly introduce two most popular quantum kernel families to set your attention. The original one, which is called Fidelity quantum kernel. Let's look at the maybe bottom first. It's just an overlap between, well, overlap squared between the quantum states, which are some embeddings of our data points. In many, well, the other way to write this theoretical value of kernel of fidelity kernel is to use a trace, and actually using the cyclic property of the trace, you can easily see how to implement on the actual quantum computer this quantum kernel estimation for fidelity quantum kernel. Well, you can first start with the initial state. It can be n qubit state, not just 1 qubit. Embed first data point, then inverse embed second data point, and project the resulting state on the initial 0, 0 state. And that's actually what is done. It also can be done with swap tests, but let's say this is the simplest way to obtain fidelity quantum kernel on the actual device. So start with the initial state, encode one data point, inverse encode the second one, and check how many times when we measure the global state at the end, we end up in the 0, 0 or the initial state. So in fact, this is a proportion estimation task, which counts how many we end up in the initial state in n trials. The second type of most renowned kernel family is the projected quantum kernel. Again, we can, okay, maybe I'll start. What's the difference? So in this case, we do not look at the global state of the system, but rather work with so-called reduced density matrices. So practically, we are not interested in a global state at the measurement, but rather at each single qubit, and usually perform some tomography of this state, which is hard on a classical level, and with this reduced density matrix of specific qubit, perform some function with a classical post-processing. This is a slightly different approach, but actually suffers the same problems. And also, when we perform this kind of quantum kernel estimation, it again is equivalent to proportion estimation. In fact, in the binomial distribution, when we perform n trials or n circuit runs, and the probability of success is in case of fidelity at least, is the kernel value. Okay, so we can let's not implement it yet on the quantum computer. Let's calculate those values of those kernels on some simulator. And when one does that as a function of number of qubits or the size of the machine that we used, there's a peculiar phenomenon that is almost always seen, is that as we increase the number of qubits, the statistical properties of the kernel matrix behave in a very specific way. So the expectation value of or the average kernel value vanishes exponentially fast. This is a fidelity quantum kernel. Okay, this is a projected quantum kernel. And the spread of the values, in this case, the standard deviation of the values, well, also vanishes exponentially fast. You have a logarithmic scale here. The same for the projected quantum kernels and almost all other kernel families. There's something different here, but that's actually states with low entanglement. They do not, at least we were not able to find this. Okay, the whole problem is called exponential concentration. Well, as you can see, they vanish exponentially fast. They concentrate exponentially fast. For projected quantum kernels, you need high entanglement to see this exponential concentration. But if you do not have high entanglement, then in many cases, those kernel families are not very useful because they can be easily calculated on a classical computer. So there's this exponential value concentration, and the problem is, it a problem? And yes, it is a absolutely huge problem, because as you can expect, if we encounter that the different values of kernel matrix elements concentrate or clump together, then our classification routine is sabotaged, because the whole idea of obtaining quantum kernel or even a kernel is to decide which pairs of points have a big similarity or a small similarity, which points are different and which are similar to each other. Okay, and if all values clump together, it's quite hard to distinguish one from another. And what is even worse, the quantum kernel estimation is not a quantum kernel calculation. Okay, so it has a limited precision, and the precision of the quantum kernel estimation is a function of how many trials or number of shots we perform. More shots, more circuit runs, the more precise our quantum kernel estimation is. So we can already expect that having this measurement uncertainty in quantum kernel estimation and exponential value concentration, well, we'll probably end up with needing to perform lots of measurements to be actually able to distinguish different values of kernel different kernel matrix values, and to have a successful classification. And we looked at this problem in some depth. I see my time, so just speed up a little bit. And we've found two effects that have to be considered when calculating how many number of circuit runs we have to have in order to have a reliable quantum kernel estimation. And the one actually introduced already in the, let's say, the original paper by Supanu Tanasi 2 years ago. They looked at probability that our measured value will lay within the margin of delta from the theoretical value, where delta is some scale of or spread of values in the whole kernel matrix, in the whole kernel matrix. And well, using just like blunt tool like Chebyshev's inequality, you easily get that, well, exponential scaling of number of runs that you have to perform. As fidelity kernel vanishes exponentially fast, this goes to 1, this goes to 1, this goes to 0, but it also vanishes in the spread. So this goes to 0 squared, and in most cases this term dominates and the whole behavior is exponentially growing. The second effect that we've realized exists is, well, the easiest way to explain it is for fidelity quantum kernels, where it might be that we'll obtain some number of shots that we need to have to satisfy this requirement, the inverse requirement, because that's prepared for the Chebyshev's inequality. So, well, it's 1 minus probability that we that we want. You have some n, but you end up with all measurements being 0 because the kernel value is so small. So you have to somehow make sure that the success rate of your measurements is, well, reasonable. So there's another just a second. There's another thing that you have to take into account, just making sure that the success rate of your measurements will be reasonable. Okay, so having formulated this this approach to obtain, looking seriously at quantum kernel estimation and believing that at some point it will be implemented on the actual quantum devices, well, we need some way to expect how many circuit runs we'll have to perform for a reliable quantum kernel estimation. And that's what we introduced actually in this paper here. So you can look at it. And why is number of circuit runs important? Well, because what we are interested in is how many resources that we'll use during the quantum kernel estimation. And the two resources that we looked at is the time of computation of a single kernel entry, single kernel matrix entry, and the mean energy consumption that will mean energy that we'll have to use to perform this this quantum kernel estimation. And we have compared that with we have to extrapolate the results, but the extrapolation is done on the number of the extrapolation is done on the level of the concentration effect, and in many cases it's a very good fit, okay, for the extrapolation. So we've extrapolated the number of the number of circuit runs, and we translated it into the total computational time and energy. The black line is for actually quantum kernel estimation with quantum error correction implemented. The dashed line is for the noiseless case. We don't care about noise, so a little bit more optimistic. And those colored dashed lines are for two supercomputers, Lumi and Henry, taken from the top 500 list. And well, we've estimated where if there's any room for advantage in the time of calculation for kernel methods. And what we see is that, well, obviously, quantum computers start quite slow, but in general, the scaling of the time is beneficial. So there's a room for speed up with respect to classical computers, but you have to look at the time scales. So for a single kernel matrix, single kernel matrix element, we have times of 10 to 10 seconds, which is like, I guess, 300 years or so. So we get, and actually it's quite optimistic, this approach, okay? We expect, we use the very naive way of computation quantum kernels on the simulation of quantum kernels on the supercomputers. So we can expect benefit of using quantum kernel, quantum devices for quantum kernels, let's say above 40, I would say above 50 qubits, but well, that's already at the time scale that is completely infeasible. Well, the same with the energy consumption. So the main message that I wanted to convey today is that lots of work in quantum machine learning really focuses on the on the machine learning performance, the accuracies, F1 scores, and so on. And in fact, I believe that so far we haven't found the robust advantage on the classical real-life data for that. But somehow the papers investigating machine learning performance usually overlook the problem of simulation time or calculation time. And in many cases, I see papers that claim that, well, with this very small circuit, they were able to find some advantage of using quantum circuit And that's completely fine with me. But it's good to remember that both in quantum neural networks and quantum kernel methods, we have this problem of curse of dimensionality or the exponential value concentration that in many cases just sabotages completely the point of having any better performance. So that's something I wanted to underline today to maybe to point your attention to trying to solve the first problem of exponential concentration, which is not an easy problem. And well, then we can safely think about the machine learning performance. So that's all from me for today, and I'm happy to answer your questions.
Okay, thank you. Great. Thanks, Artur, for a great presentation. I see one comment from Jacob. The problems you are facing in QKE are high dimensionality problems. There's a question from Ravi. Could you say that projected QKE estimation provided faster computation than fidelity QKE estimate? Also,
Okay,
qubit scaling is an important factor.
That's a great question. Just a second, because I just have to enter full screen again because I've thought to look at the chat, but that sabotages the sharing. Okay, so the comparison between projected and fidelity kernels, right? From
Yes.
the computational time. Okay, so the first thing is, let's observe the top panel is fidelity quantum kernel, the bottom panel is projected quantum kernel, and I've set the scale to be the same on both of families. So the thing is that you can already see that for fidelity quantum kernel, this exponential value concentration is much more severe than for projected quantum kernel. So that's a general statement. Even I've heard it from in a private talk with Supanut, who first pointed this problem in his paper, that, well, fidelity quantum kernels, they do not perform well with respect to the resources, and rather should be dropped. That's in general the statement. If I have time, I would like to just address why there's different scaling, or why one type of kernel concentrates and the other type of kernel also concentrates, while they are obtained slightly differently. So very intuitive explanation. For fidelity quantum kernel, we just look at the global state, and this very particular state that we would like to obtain after measurement is in high dimensional spaces. And in the case of kernel methods, we have 2 to the n. The dimension of the space is 2 to the n, so very large. There's a very small probability that after encoding the data, let's say we do it in such a way that it covers well the available Hilbert space, there's a very low probability that we'll end up with a non-zero overlap with this global state. So that's why fidelity quantum kernels concentrate, intuitive way of understanding. For projected quantum kernels, that's slightly different. And the problem is that we would like to embed the data in a highly entangled systems, and let's say loosely speaking, most of the information is encoded in the interaction between the subsystems. But what we do in here, we actually trace out or average out the interactions between the subsystems. So in fact, what we get in the end is the reduced density matrices, which are in most cases very close to maximally mixed state. So they don't remember about the initial data. So they are basically all the measurements leads to very similar states. And if we use, for example, the subtract one from another, it very easily goes to 0. Okay, so those are the two mechanisms. And in general, for projected quantum kernel, the issue is a little bit less severe, but it still exists.
Okay. Jacob wanted to ask a question. Yes, please.
Yeah, thanks. That was a very interesting presentation. You could see a lot of parallels with my presentation early on, which you missed.
Yeah, I'm very sorry, but somehow family
That's okay.
obligations.
Because I looked at virtually the same issues, except that it's not even related to quantum systems. It's just purely dimensionality. And I was going to
Yes.
point out that the first obviously have a global measurement, and so it's to do with the measurement.
Yeah, it's a direct curse of dimensionality in here.
Yeah.
Exactly.
So,
It's purely classical, I would say.
Yeah. So that's actually well done. It's the second I was actually going to say it must be to do with high entanglement of your unitary. So it's a black box, but it doesn't show there is a lot of entanglement inside. And so that's actually slightly misleading in a sense, because the problem is in that black box rather than in the measurement. The measurement is not problems here because they're independent.
Yes, that's true, but somehow the what's inside the black box influences directly the number of measurements we have to perform, right? So that's the logic of thinking. And okay, the statement about black box is that, well, you correctly pointed out that's the problem with entanglement. That's completely true. But so we can say, well, okay, so let's take small entanglement systems like those here, and the problem vanishes. Well, yes, but on the other hand, we can easily simulate those on classical computers. So we will not be able to beat classical computation with well, it's a very general statement, okay, but loosely speaking, we'll not be able to beat classical simulation with systems with low entanglement.
Yes, I have another comment, because a lot of those issues that we talked about here is all because of dimensionality.
Yes.
Currently, Qiskit is battling those issues because now they work on IBM machines which are over 400 qubits. And so they have directly problems with measurement. So they used a lot of techniques for like binning of measurements, because otherwise you have zeros returned everywhere.
Yes.
If you measure too many, you don't have enough
zeros or noise, basically.
It's a sampling problem, basically. You don't have enough
Yes.
samples to fill it up. So that's why you need to bin it, and you need to bin it early on. Otherwise, later on, you still have global measurement. So you can't measure globally and then bin it. You need to do it early on. So grouping of qubits and so on. So there's a lot of new techniques they develop. They completely redo Qiskit because of very large quantum machines. And we could learn a lot from what they do currently within Qiskit.
Mm-hmm. If you have some nice references with this work that they are actually struggling with this and trying to compete with that, I'd be very glad if you can
Qiskit does not have a lot of documentation. So.
Yeah, well, that's a very well-known problem with Qiskit, and especially the different versions of Qiskit, how they work.
But I had a good summer course which specifically looked at programming the new quantum machines. So problems with error mitigation, but also problems with large circuits.
Yes, absolutely. So
it's a different world. So we still think in terms of stitching circuits to solve problems. This is not going to happen like this. So kernel methods are fantastic, but they, as you point out, they battle those issues right now.
Yes, and actually there are some kernel families that claim that do not exhibit exponential concentration. There are quantum quantum Fisher kernels, but I would say it's always either exponential concentration or the classical simulability. And in the case of Fisher kernels, they are just, let's say, they use symmetries that can be also utilized by classical computers to calculate those kernels faster.
Thanks a lot.
Okay.
Yeah, thanks.
We need to move to the next talk. So Artur, thank you once again. Jacob, thanks for asking the question. Thanks for the interesting discussion. All right, and the next speaker is Nouhaila Innan.
So, hi everyone, I'm Nouhaila Innan. I'm a postdoc at NYU, New York University, Abu Dhabi campus, and I'm working on quantum machine learning. Yeah, so first of all, thanks, Paul, for the invitation. It's good to be here after like attending last year events. So, today's topic is like exploring quantum machine learning and quantum federated learning for financial fraud detection. So it's mainly like kind of like application of quantum machine learning in finance, especially fraud detection. But the main objective here is not to beat classical or say that quantum is better, not at all. Like at this time, still like for classical, they are really good with classification, especially when we are dealing with real data sets. But still, like it's kind of like explore if quantum can achieve like high accuracy, and also explore other metrics that can show maybe some potential, like from computational resources or any other metrics, rather than just like the performance. So yeah, so I will skip like quantum machine learning, as there was like, I think, a lot of slides about quantum machine learning. So I will go directly to the application, like what's the motivation behind applying finance in quantum machine learning. So it's good like to start with understanding the scale of the problem. So in 2018, worldwide credit card fraud loss amount like more than 27 billions, and between 2017 and 18, there was like a 60% increase in credit card fraud, with the projections suggesting that the loss could reach more than 40 billion by 2025. Yeah, and with this scaling and with the statistics, like the question that can arise, like how can quantum machine learning help in stopping the credit card fraud? Of course, like classical is doing a lot of stuff, but still like it can be a good approach to see how quantum machine learning can be evolved. So usually for finance fraud detection, the process always starts with the terminal check, where essential verifications such like correct PIN and sufficient balance, card status, if it is like blocked or not, are conducted. Then the transactions that pass these initial checks proceed to a predictive model. Of course, like in the previous years, like it was only machine learning, and right now we are trying to introduce here quantum machine learning. So to assess like the fraud risk, then this predictive model evaluates its transactions and assigns a fraud score. These transactions flagged as high risk are rejected immediately, while lower risk transactions undergo further security feedback, like from the process, including the outcomes from investigators who review this suspected like fraud cases. Then this loop back to refine and improve the predictive model continuously. So this kind of like cycle ensures the system becomes like more robust and accurate over time. It's like kind of training, enhancing its ability to detect and prevent fraud effectively. So this is for classical or quantum or any type of machine learning model that can do the classification. Okay, it's not moving. Okay, yeah. So now moving to an overview of like the approach that we employed, like to assess the efficacy of like the different variational quantum machine learning models in detecting the fraud with two different data sets. So of course, like the process begins with data processing, where techniques like such like topological data analysis and principal components analysis are used to encode the data effectively. Then this encoded data is fed into different quantum machine learning models. Here we use like quantum graph neural network. And this is like the first approach, and we studied the effects of like the number of qubits and the hidden layers. Then for the other approach, we use like different quantum supervector machine, variational quantum classifier, and estimator quantum neural network and sampler quantum neural network. Then we study here the effect of the feature map, the type of encoding. Then for the output, of course, like at the beginning, we were just like trying to see the performance. So we focus only on the performance metrics for binary classification, which is like the accuracy, precision, recall, and FR score. And for this, I think, yeah, let me go to the dataset. So for the dataset, there was like 2 datasets. So this first one is credit card transactions, which is kind of like, both of them kind of like similar, but this one is like more realistic because they use kind of like a based, they didn't give much details, but most of them like are like from real data scenarios. And the problem with this data set, it's so unbalanced. So we had to add like more metrics to make sure that the classification is good. And we use here like quantum graph neural network. For the second data set, we use like the other models, which is quantum supervector machine, variational quantum classifier, and estimator and sampler quantum neural network. Now moving to quantum graph neural network. So it's just like any quantum machine learning models. This one is like extend the graph neural networks by using quantum circuit to process and analyze graph structured data, improving efficiency and scalability. I would say like potentially. But yeah, this is the, this is the architecture that we use. So we try like to integrate both like the classical and quantum. So this integration aims to capture like complex relationship and patterns among nodes and edges more efficiently than other existing works in quantum graph. So the process starts with like feature compression, which is like the input graph data undergoes feature compression, then reducing the dimensionality while trying to retrain the essential information. Then we have the data encoding, as always, like I will explain more in the next slide. Then we have like the variational quantum circuits. The encoded quantum states are processed through this variational quantum circuits, and we try to optimize the transformation of input states to output states. Then we have here an average pooling. So this average pooling is like aggregates the processed information, enabling efficient handling of graph data. Then we have a linear layer. So this pooled data is then fed to this layer, which finalize like the output for the desired task, the classification, either 1 or 0, like fraud or non-fraud. Then of course we have the optimization loop, which optimized like through the variational quantum circuits. Yes. So regarding how we did that, like for the implementation. So yeah, we started with extracting the graph features and relational data from the transactions. And each transactions is transformed into a graph where the nodes represent the transaction attributes and the edges capture the relationship between these features. This is done only using classical approach, which is the topological data analysis. Then this structure representation enables to the model to detect like hidden fraud patterns than the traditional methods, which is like directly just like do the pre-processing, then go to the feature encoding. So after that, we implemented like, we tried like to encode this graph into the quantum data. And we use like angle-based encoding for feature transformation. Then we converted the classical graph into a quantum compatible format. Specifically, each node feature are encoded into the quantum state using rotation X, Y. This step ensures that the quantum circuits can efficiently process the transactional graph data while using the principle that we want to use, like superposition and all of those. Next, we set up like an iteratively and adjust like the quantum circuit. This is the circuit that we are using. And the idea is like we need to train to optimize the feature transformation until we get like the higher accuracy. And during this training, the circuit's parameters are updated iteratively to improve the fraud classification accuracy. Then, of course, the circuit is executed to derive like the quantum state as model output, as we mentioned, like from the linear classifier, sorry. Yeah. Then moving to the second approach, which is like using different models, starting with quantum variational classifier. So also quantum variational classifier or any quantum machine learning, they have always the same pipeline. It's like it starts from encoding, then the answers, then the measurements, then you do some optimization. So here it's the same thing. So it integrates like classical preprocessing with quantum feature mapping. And the idea is like we have this optimization, we have a loss function that we need to optimize, and we use like classical optimization. So I won't go into the details. Yeah, here quantum super vector machine, Artur like try to explain it, use like the kernel, it's the same. So quantum super vector machine, they are all trying to use like the kernel methods. So here we encode the data, then we have this, we try like to find the similarities between the two operators. So it's like similar, what we call like the kernel trick. So it's similar to classical. So this quantum super vector machines like use a kernel function to transform the data into a higher dimensional space where it's easier to perform the separation or the classification. But however, like in the quantum state space, for like usually we try like to look for potential exponential speed up or in finding this optimal hyperplanes like classification. But yeah, based on the result, it was good, but like I will go into the details. Now for the quantum neural network, we use like two different types, which is sampler and estimator. It was from Qiskit. So starting with the estimator, so this architecture involves like a unitary operator applied to quantum states, which are then measured like any other, like the other quantum machine learning. But the here the sampler is like try to extract like the samples from a quantum sample and sampler and use classical methods to select the best solution for the task at hand. Then it optimizes the parameters. And we did a couple of modifications for this original architectures, just like kind of like make them adaptable to our data sets. And the idea here, like the difference between these two is like samplers are kind of like primitive unified blocks requiring like quantum resources to efficiently produce the output. Well, the estimator is based on the evaluation of the quantum mechanical observable. So yeah, and another thing here, like these samplers are responsible for accepting like the quantum circuits, or like what we call like the sweeps of value over the parameterized circuits, and sampling from their classical output resistors. And here, well, like the estimators accept like the combination of these circuits and observable to estimate the expectation values of this observable. Yeah, and for like the implementation, so of course we started with preprocessing and splitting the data sets. It includes like cleaning, normalizing, and splitting into training and testing. For the configuration of data encoding, we use like 3 different ones, which is like very famous. Like they are all like angle encoding, but different architectures. So we have like Z feature map, which is like more simple one. Then we have poly feature map, then double Z feature map, and they have like some arguments or like functions there, like number of repetitions, like type of entanglements. We use like different ones until we find like the best one. So this like transform the classical data into quantum states. Then we have the configuration training for the quantum models. So we use like the different circuits, like we try like to use different circuits of the three models that we are using, variational and quantum neural network and quantum supervector machine. Then we simulate the quantum circuits to evaluate their performance. Then the performance evaluation, as I mentioned, here we use like different metrics, which is like accuracy, just like the performance metrics. Now moving to the results, starting with the graph quantum neural networks. So the left like graph, it's 6 qubits with one hidden layer. So here we see the training and the validation loss for this configuration. And we observe like successful loss reduction over epochs, indicating that the model effectively learns from the data. Of course, there is like some zigzag, but it should be fine based on like because like we took like around like 5 around like the average of 5 runs. Then the right graph here shows like the training and validation loss of the configuration with 2 hidden layers. And it shows also that the model in general demonstrates like effective generalization without overfitting, as indicated like with this steady decline and stabilization of the loss. So in general, these results highlight that this model, quantum graph neural network, has the capability to manage the complexity and maintain performance across different architecture, proving its robustness for the fraud. Yeah, and as I mentioned, we try like to study the effect of like the number of qubits and the number of layers. So for the first configuration, it achieved the highest accuracy, 0.94, and F1 score, which is like 0.86. So it make it like the optimal setup over all the other configurations. Well, also like 16 qubit shows like good accuracy, but it's not like the other ones. So the idea here that the optimal configuration for the quantum graph neural network balance like the number of qubits with hidden layer depth to maximize the performance. So here it shows like using a minimum like 6 qubits with 1 hidden layer setup can be the best option. And of course, like usually when we use like a small number of qubits, we don't have like a lot of noise and different problems like parent plateaus. So that shows somehow like if you are talking about like a very small scenario, so using a small number of qubits can be helpful. So as I mentioned, like the data set wasn't balanced, so we had to do more, which is like to check like the precision recall curve for the optimal configuration. And here it shows like the EUC, area under curve, is like 0.85, which is like highlighting the model robust discriminative power. So this value indicates that the model effectiveness in distinguishing between the fraudulent and the legitimate transactions within an unbalanced data set. And here I would say like the model's ability to maintain high precision across varying levels of recall further validates its efficiency in identifying like fraudulent activities and without generating excessive false positives. So in summary, for this quantum graph neural model, it shows like strong potential for practical application in finance fraud detection, especially when we are dealing with unbalanced data sets. But yeah, it doesn't mean that we can beat with this model like classical models. Classical models for financial fraud are still better and better. They can achieve like higher accuracy and higher UC. Now moving to the second approach, which is like using different models with like different feature map. So starting with this, so the first figure here like displays the convergence of loss function for the variational quantum classifier. And we can observe like effective learning as the loss decrease over the iterations for the 3 features map. with with C feature map here, like the red one, shows like the minimum loss. Moving to the second one, which is like the estimator, quantum neural network, which also shows successful loss reduction, confirming its learning capability. The third one is like for the sampler. Also, you see that there is like a convergence, but like Z feature map shows like faster and more minimal convergence. So, and yeah, there is like no quantum supervector machines model, because like usually because we use like some pre-built functions, and this one doesn't include like the callback function to plot the loss. So usually in quantum supervector machines, not always the case. So here it just shows that the model is learning, and we will move to the accuracy of these models. Yeah, so, and based on like, we focus only on Z feature map, but you have the paper, you can check like the performance of all the other feature maps. So here, like, we have the accuracy, precision, recall, and F1 score with QSVM or quantum supervector machine classifier achieve like an impressive F1 score, which is like 0.98, highlighting its superior performance. Also, like variation quantum classifier was good. But yeah, so the idea here, like the metrics of like for Z feature map were the highest comparing to the other feature maps. It shows like also somehow like this effectiveness enhancing the model performance. But the question like that we can ask, like, why is that feature map like performs better? So just like if, like, let me go to the previous slides. So here's Z. Yeah, sorry. Here. So here Z feature map is like a very simple feature map. It doesn't involve a lot of gates. So technically, this simplicity reduces like the potential for noise and error accumulation of the quantum circuits. So the straightforward structure of Z feature map leads to faster conversion during the training, as it requires only fewer quantum gates in operation. Now moving to quantum federated learning. So this is like the potential of quantum machine learning in like for finance. It shows that there is a potential and there is like some really good, like from the accuracy, there is like good performance, but still like if we want to use quantum machine learning in real scenarios, especially for the banks and all this quantum machine learning, they are models, they are not private or they are not secure. They can achieve higher accuracy for now, but still, like for institutions that they need like to protect their data, it won't be that useful to use quantum machine learning model. So yeah, the idea is like handling sensitive data, whether like it's personal, financial, or healthcare related. It will require like a robust framework that ensures like privacy at every step. And with quantum machine learning, we are not just talking about using like this technology to solve like problems, but we are also, or we want to ensure that this technology protects the very data it's designed to analyze. So, and as a solution, there is like quantum federated learning, which enables like multiple parties to collaborate on quantum machine learning models without ever sharing the underlying data. This means that while the model learns and improves, the sensitive data remains secure and private and intact. So privacy is not like afterthought, but like it's essential, especially when for like the finance data and this or healthcare. So what do we mean by quantum federated learning? So imagine like we have several hospitals or banks needing to collaborate on improving their models. It can be like this is done classically, just like instead of the classical machine learning, we use quantum machine learning. So usually or traditionally, they would have to pool their data and raising concerns about the privacy breaches. But using federated learning or quantum federated learning, it can eliminate this risk by allowing its institutions to train their models locally on their data and then only share the learned model parameters. They don't have to share their data itself, just like the parameters. So with this approach, it preserves like the privacy and enhance the model robustness by integrating diverse data insights. So this technique ensures that the benefits of like collaborative learning are realized without compromising the data integrity or confidentiality. Yeah, and we try to apply that for financial fraud detection. So yeah, the process starts with like the initializing the model parameters randomly and each of the end clients. So we can have like multiple clients receive a local copy of the model and train cures independently of their distributed data set. Then for each local model iteration, the data is first like encoded into quantum states. Here we use angle encoding. So technically it's the same as quantum machine learning, but the idea is like we have the local and the global model. And this is the circuit that we use. Yeah. And the local model, of course, use also optimization. We use like here the mean square error to calculate the loss. Then we optimize like via Adam optimizer. And the clients continually like train and validate their local models. Sorry. And there is like some existing early if convergence is achieved. And once this local training completes, optimized parameters from each client are sent to the central server. At this central server, these local updates are aggregated to refine the global model. So, excuse me. Yes, so yeah, at this the central server, we have like the local updates are aggregated to refine the global model, which is then redistributed back to all the clients. This iterative process continues until the global model achieves like a good performance. Here, this federated setup ensures that the data never leaves the clients, preserving the privacy while still benefiting from global model improvements. And also here in this case, we use like just like identical and independent data. And we have like some sub data sets across the clients. And like this, we ensure that we have like a uniform training condition without centralizing sensitive data. So yes, and for the dataset, we use this IEEE CIS like fraud detection datasets, which include like both identify and transactions data linked to transactions ID. We then like process the data by optimizing the memory uses, handling like missing values, and then applying one-hot encoding to categorical features. Then of course like standardization like of numerical ones. And to address the class imbalance, we apply like upsampling for better fraud detection. So we use Penelane for the quantum model, and we also use Qiskit to simulate the quantum noise to create like kind of like a realistic quantum computing environment. The model operates with like 4 qubits and use, as I mentioned, Adam optimizer with a learning rate of like 0.1. We train like locally and globally over 100 iterations across like 15 clients. And we evaluate like the model using metrics like the performance one, accuracy, precision, recall, F1 score, and the loss. So yeah, starting with the loss. So this is the validation accuracy in the loss trends for our framework. So this is average like over 10 trials or 10 runs to ensure the results reliability. So initially the model starts with like an accuracy of like 0.73 with steady increase reaching a plateau of like 0.95. And remains like consistent beyond that point. This plateau reflects that the model's strong and stable fraud detection capabilities, and also it shows like this is the maximum performance that can achieve. Simultaneously, like the validation loss shows like significant drop from 0.27, I guess, to 0.02, highlighting the model's improved precisions in distinguishing like between the fraud and legitimate transactions. There is like a key learning phase occurs between like iteration 1 and 20, where we see the most notable improvement in both like the accuracy and the loss that demonstrate like the model effective convergence. And this sustained like high accuracy and low loss post iteration around like 35. It shows like the model's robustness, performance, and the reliability in fraud detection tasks. And also suggests like some potential implementing an early exit strategy, allowing us like to reduce the computational costs without sacrificing the model performance, which is like crucial in resource intensive like quantum environments. Yeah, so here this is like the validation accuracy trends across individual clients. It reveals like important aspects of the framework on the distributed dataset. As shown here, like the initial variability in the accuracy suggests that each client model interacts differently with its local data, influenced by the unique characteristic of the data and the stochastic element in the training process, like the random initialization and the adaptive optimizer behavior. And as the training progressed, the result shows like a clear convergence pattern by the 70 iterations. The validation accuracy of most clients stabilize, with the majority achieving like accuracy levels around or above like 90%. So this indicates that our framework successfully synchronized like the learning trajectories across the distributed clients. It's not like one client is achieving better accuracy than the other, but it's like lead to a consistent and robust overall performance. And this increasing mean accuracy are shown in the trend line. So, and this caused that this framework ability to harmonize like the client models, even in decentralized settings. So despite like the overall positive trend, there is like minor fluctuation in accuracy. This is like for some clients, particularly in the later stage of the training. So usually this fluctuation likely results like from the heterogeneous like nature of the data across clients or of the sensitive individual model to specific features. Will this variation do not detract significantly from the overall convergence? They highlight like the necessity of like continuous monitoring and potential fine-tuning to ensure that all clients achieve like optimal performance. Now moving to the noise. So in this experiments, we subjected like the framework to various quantum noise models, which we call like the quantum channels, to simulate real world scenarios condition. So we started like with the polarizing noise. The model maintained like a strong accuracy of 90%, but showed like its tolerance limits at accuracy dropped like at 0 when the noise parameter reached the maximum. Moving to another model, which is the bit flip. So here it shows like notable resilience, but it sustained like a high accuracy at the beginning until the noise parameters hits like 0.3, after which the performance gradually decreased again. reaching like 0.8 at the highest noise level. It means it's still like good, but it shows like the model strong error tolerance to bit flip errors until a critical threshold, where like the other, for example, amplitude damping noise, the accuracy decline was more gradual, falling like from 0.79 to 0.4, while the fuzz damping had a more severe impact, reducing to just like 0.09, highlighting the model sensitivity to fuzz perturbation. So overall, this analysis highlighting that this model or this framework varying like sensitivity to different noise models, which it demonstrates strong resilience in some cases, especially against like the bit flip and fuzz flippers. It remains like vulnerable to fuzz damping and the other one. So these insights are crucial for guiding future quantum error correction strategies to further enhance the framework robustness, particularly as like quantum technologies continue to mature. So here, of course, like in the real scenarios, we don't have like only one type of this noise, but we have like a mix of all these noise models. So the next step should be like add more error mitigation techniques that can enhance more the performance, even with like noisy quantum computing or computers. Yeah, so this is so far the conclusion. So in general, quantum machine learning shows like significant potential to improve like or achieve like good performance in fraud detection. And model like quantum supervector machine and graph neural network shows that they are good for classification and for real data set scenarios. But the thing is, like, if we are trying to compare classical versus quantum, it won't be that good, because like classical machine learning for fraud detection or binary classification, they can achieve like 100%. But the idea here is to show, okay, this first step is to show that the quantum machine learning is somehow working. Yeah. So this is the potential. It's working now, like how to improve it better. And the other thing is like to show where is the advantage. So I would say like all of us try to find like why we need quantum, what's the advantage of using quantum. So this is like, we need to find the right metric to show this advantage. Or even like we need to define first like the advantage. So maybe like from the computational resources, or maybe from the scalability. So if we increase the complexity of the problem, we might find like that quantum can be better. But yeah, at this stage, we are not trying to beat classical. So we are just showing that quantum machine learning has the potential to solve like real world scenarios. Of course, like we need to use more qubits with more data samples. But yeah, it's like, this is just like kind of like proof of concept. And yeah, that's all from my side.
Guys, so I'll be talking about quantum machine learning, automated quantum machine learning as hyperparameter optimization, in a sense to be explained during the talk. I will be basing this talk on the joint work with Piotr Gawron that we did for the Euro HPC-PL project. So this will be a piece of software that we actually developed, and it's available to all of you, named Accumulator, as you can imagine. And it is meant in its core for non-quantum machine learning practitioners, meaning that if you have absolutely no idea how to handle quantum machine learning models, or even how to handle quantum computations at all, then you should in principle be able to use this platform and make your part of your machine learning pipeline a quantum machine learning one. I will show you how to do it in a second. I will start with the short introduction. Maybe I'll skip most of it just to get some notions, so I can discuss it further during the talk. Then I will go with the high level overview of the platform that we developed, so how it works and why we can do such things. Then I will show you how to use this general approach, like this piece of software, and show you the examples. If you are interested, we actually have a paper about this platform. It's currently on arXiv, soon to be on the Computer Science Journal. Okay, so as most of us already mentioned, there is this quantum machine learning basically boils down as of now to the stuff when you do some optimization on the classical computer, you don't specify the control of the circuits and so on, run it on a quantum machine, and then process the measurement results again on classical computer, and you do it in a loop, so to speak, right? And what is done on quantum computer is actually a three-part step. You prepare the initial state, then you evolve it, and you get the measurements, right? We all discussed this already. But what is maybe an important, and actually what Jacob said, an important factor here, building on the scheme that Paweł showed us at the beginning of this conference, there is this the way to depict the ansatz, right? So you have this unitary, possibly made of different smaller unitaries, that is used to evolve the circuit, right? When you go to this diagram, when you have this preparation, evolution, measurement, preparation is usually just setting the qubits to zeros, right? This is done automatically by any platform. Then you evolve it, so you can encode your data, you can encode the weights of your set, like the standard stuff we already discussed. But what is important here is that you can actually re-upload the data, and you should actually re-upload the data, meaning that you should encode the data multiple times during the execution of your circuit, because it has been shown to make the expressiveness of the quantum machine learning model better, a lot better. Okay, so this is important. You can see this Maréchal paper or the one that Jacob pasted in the comment. Okay, so this is one thing that differs from the Paweł. So this data uploading stuff, really important, guys. Okay, so there is that. And essentially, when we think about quantum machine learning, you think, or even quantum computing, really, you think in this gate-based model, because there are different paradigms to quantum computing, right? But when you think of gate-based quantum computing, you essentially think that a building block of quantum computing scheme of algorithm is a single gate, right? And usually that's a good way of thinking, but instead you can think bigger. You can think that a building block can be larger. It can consist of the whole layer, be it a variational layer or uploading, embedding layer. It's just a matter of what you really want. But what I'm saying is that you can consider such layers as a basic building block. And it has been shown that some layers, some designs, some ansatz work pretty well in general approaches, okay? So this is important because we can use this information later, okay? And I will show you how we can use it basing on the accumulator, so this auto quantum machine learning platform that we developed. The idea here, as I mentioned before, is to have the non-quantum computing people be able to use quantum machine learning models in their pipelines, like as a part of it, as a whole, however they please. And it was important to us to be able to have it implemented in the current pipelines. Therefore, our models, the one generated by accumulator, can be extracted to PyTorch and used with PyTorch. They are in line with SKLayer models, mixins, or the API in general, right? So we can use it. It's open source. You will have the address later. And it's a black box approach, meaning that you don't really have to look inside it. You just have to call some functions and the model will be given to you. I will show it in a second. It requires no quantum knowledge at all, in principle, okay? what accumulator can do, it can actually make a lot of usual solve or find models that are trying to solve the usual general machine learning tasks, meaning that the classification, the clustering, this is actually done by adiabatic computing, not the gate-based one, but that's detail. You can do the standard linear regression or even multi-label classification, but this one actually would require some gymnastics. I will talk about it in a second. How accumulator does it is basically you in a broad scheme, when you are using this whole architecture with the SLARM and so on, you basically log in, you put the data that you want to process, and then you submit a learning task. So we are saying, okay, given this data, I now want to, I don't know, run the classification on it, right? So who is drawing on my presentation? Sees it, please. Then what you do is you can submit this learning task and queue it, send it to the quantum resource, right? And then just infer and repeat this standard, this one procedure. So control, update, run, measure, update, blah, 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 so on, right? And what is important here is that you actually have a very, as short as possible window of using the quantum resource. Meaning, and the quantum resource here can be interpreted either as a real device or as a simulator. So we don't want to, have it. We don't want to have it occupied if we don't have to have it occupied. That's why this is quite a neat approach. And then after we are done with the training, with the inference, or with whatever, we just get the results and the task is done. Okay, so that's how it works on the high level. So essentially, what we are saying is you're getting a task. So for instance, classification, right? We check if the data that you gave with the for this classification is valid, meaning that you have the right number of labels, the right number of features. If the mob, that's it basically, I think, if I remember correctly. Then the model is proposed by accumulator, by the platform. We train the model, we test how it works, so we basically evaluate it. Guys, please. We check if the model works. Paweł, could you please try to handle the drawings? I don't know if you can.
I will try, but I'm also not sure if I can.
Yes.
To do it. Yes.
Okay. I will proceed with the with the scribbles. If the model is best, we save it, and then we try to find another best model. Unless the budget is exceeded. Budget here meaning that we can have limited time access to the quantum resource. We can have a limitation on the number of shots that we want to do. We can have a limitation on the time. It depends how you specify it, but it can in principle it should be done. Okay, Paweł, I handled it. Don't worry about it anymore.
Okay.
So there we go. After this is done, so after the budget is exceeded or you found the satisfying results, we return the best model that we have found and we report how the training went. So you got all this log about what happened. Okay, so that's it. And as you may expect, this stuff that the quantum machine learning really, automated quantum machine learning really does is basically having it's not a new concept. Like you could imagine that people already tried to do quantum machine learning in an automated fashion, because automated machine learning is a thing in the field. But there are actually quite a few tasks that could be done with the that could be considered automated quantum machine learning, meaning that you can have this aforementioned quantum architecture search. You can have this hyperparameter optimization stuff. You can have something that is called here quantum resource awareness, meaning that this approach can consider the limitations that you have on the resources. So the simple number of qubits, the shots that I talked about, and so on. And the model search, meaning that you can have different kinds of models, like quantum neural network or this kernel stuff that we discussed. Actually, accumulator does the both. And only accumulator, as far as I know, checks all of those things. You can do the model search, quantum architecture search, hyperparameter optimization, and quantum resource awareness. And it is one of only two solutions that are open sourced. Okay, but you now know like the idea. How does it really work? What in principle it does? As I said, you can consider the layer as a basic building block of your machine learning model, right? And if you do so, then you can think of it as you can think of an ansatz finding, this quantum architecture search, basically, as an hyperparameter of your model, right? So you are thinking, okay, I want to use a quantum neural network for instance, classification task, but what architecture should I use? And I'm saying, okay, your architecture is basically an hyperparameter here. The layout of the layers is a hyperparameter here. So you can use standard hyperparameter optimization libraries to try and optimize those hyperparameters for you, right? And yes, so this is the whole idea. And how we can do that is we can actually take, for instance, Optuna. In accumulator, we use Optuna, so the standard hyperparameter optimization library, to find the layouts, quantum architecture search, basically to do the quantum architecture search based on the whole layers for the model that we want to use. And Optuna has a lot of different features. For instance, there is this parallel processing, there is this dashboard that can visualize the results of the training. So it is pretty neat tool to know. And that's exactly what we do in accumulator, and how quantum machine learning can be considered a hyperparameter optimization. Actually, the same goes for the type of the models, meaning that if you want to do classification with quantum embedding kernels, for instance, it is also available, and it's also a hyperparameter. You're just saying, I want to do classification, I don't care about the model. And if you don't care about the model, then Optuna will try all the models that are basically available to it. Okay, so how, when you go to the code-wise usage of this, you basically have to import the relevant stuff, prepare a classifier finder, which is a model finder. So for instance, I'm saying, okay, I want to do a classification. So this is my task. So I'm creating a model finder from the accumulator. I supply it with the features, with the classes, and with some additional hyperparameters. So describing the resources, for instance. So the number of cores that are available, the device that I want to run it on. It actually works with both Qiskit and with Penlane Simulator. So there's that. The number of seeds, the number of epochs, just standard stuff, right? Then what you do is just run find me a model. Same goes for hyperparameter tuning. You just supply the classifier that you have found here, for instance, the data, and you run find hyperparameters for it. That's all the code you need. This is actually the code that I used in my unit tests. But that's how it runs. It's just that simple. I told you that accumulator will try to use the layers that are available to it. It just means that you can specify what, for instance, data embeddings you want to use. So if you want to use angle or amplitude embedding, the default and standard ones in the field, implemented by default in Penlane, for instance, and I'm using Penlane here, you just have the constructor for angle embedding set up in a specific dictionary. You just specify the other one. You can specify your custom ones if you wish. And after you append this data embedding dictionary, you can also append the data layers and so on. Quantum layers dictionary and so on. It's simple enough. It's just in one of the config files that you can see in the accumulator. The accumulator will start to use those embeddings, those layers, those whatever tweaks you have. Okay. So let's see it on an example. I wanted to run a binary classification on this synthetic Moons dataset. So we've got two classes that are not linearly separable, and I wonder if I can classify them, right, up to some accuracy. And what you can see here is that accumulator ran, because that's how many I specified, 10 different trials. So it tested 10 different models, only 2 of which were completed. Completed meaning that they achieved 85 accuracy, the accuracy, 35% accuracy on this Moons dataset, which is the one that I specified that I want to obtain. And only 2 of those were accepted because they, did go over this threshold. And one of those was selected because it has lower number of quantum machine learning calls needed, quantum resource really, calls needed to obtain such results. Okay, I can then check what are the most important parameters that were that defined how accurate the model was, and it turns out that the model type didn't care at all. That's true because both of those are quantum embedding kernels, and quantum neural networks wasn't the simple ones wasn't able to obtain this accuracy. And the most important layer were the second one, so perhaps was a difference between those two. I really can't remember. This is very, very old picture. Yes, and you can see that the number of quantum resource calls dropped for this second model, and that's why the second was accepted. And good news for you, I actually pulled an all-nighter yesterday or today, should I speak, so that I was able to update accumulator so that it now works with the latest Penny Lane and Qiskit versions without any issues that I could find, but I've got a lot of unit tests, so I think it should work well. So the version 0.2.0 is available to you via pip, via repositories, I will show them in a second, and via and documentation is available via read the docs, which is kind of great. In the upcoming version, I actually plan to upload to defaultly implement more data re-uploading layers, some more default quantum layers that I want to use, MLflow support to those who are familiar with this library. It's really great. And I'm actually in the process of testing this on a real problem related to what Artur actually talked about, because this is for change detection on satellite images. So we'll see how it works soonish, I hope. And that's basically it, guys. So to conclude, what I'm showing you is the piece of software and an approach. A piece of software is implementation of the approach, and the approach is basically, you can think of quantum model search, quantum architecture search as a hyperparameter optimization problem, up to some limitations, meaning that you can't really have you have to use bigger building blocks. You can use it without any quantum machine learning or quantum computing knowledge. It is available to you open source. You can modify it. You can do whatever you please with it, and you can use it in your current pipelines and using actual real existing quantum devices. All the addresses for me are here, and all the addresses for the library are here, and they are actually updated, as I said, several hours ago. That's it from me.
Great, thank you. Thanks, Tomasz.
Thank you.
Yeah, we already have some questions. So in particular from Sebastian and Jacob. Sebastian, maybe you can unmute first. The question is, how do you proceed with input data? Feature selection, yes. Standardization. Mm-hmm.
In my case, we got some, we can do standardization here. We can do, I actually don't remember that much of the details because I tested accumulator as far only on the toy example. So they were, pretty well behaved, so to speak. But the point of this this framework wasn't really to handle all the machine learning pipelines, so to speak. So the assumption here is that you preprocess the data by yourself. So you can't input trash in accumulator because it will probably blow up. But assuming that you have well-behaved data prepared in a fashion that you want it and you think it should run, then it should work fine. I can check and send you the details, Sebastian, about what is like how accumulator can help with processing the data, but I would have to refresh that. So sorry, I can't answer it right away.
Okay. There were also 2 comments from Jacob. Jacob, would you like to also ask a question or?
Okay, I first of all, a comment that this is very impressive. The software works with recent version of Qiskit because nobody else could do this in the world, including Qiskit people, machine learning. They still can't do it.
I actually, that's why it was an all-nighter for me. The Qiskit had a lot of problems. So yeah, I agree.
Right. But the second question is, Classic, the Israeli company, because they have a few years over you to do this automatic model generation. But the question really is, can you actually stick to a single method of synthesizing your models? Because they don't. They have various techniques to handle very different situations.
What do you mean a single method? Because if we are on this, upper level, when I'm considering hyperparameter optimization as a model finding method, then I am throughout all of the framework, I'm using a single method. But if you are saying single method, meaning that, for instance, I want only to search for not quantum kernel related, but only, I don't know, quantum neural networks related models, then it also can be done, but you have to limit
for example, they handle optimization of hardware. And I don't know if you can squeeze it into hyperparameter optimization. They probably needs to have specific tasks that need to be done in a very different way.
I am still not sure if I follow, because I agree that different models require different handling. That's absolutely reasonable thing to say. And let me maybe go back because that might highlight what I'm thinking. See, angle embedding, for instance, and amplitude embedding have different kinds of the parameters that they use in order to use those layers, right? So as long as you, when specifying what you can use, as long as you specify the hyperparameters, or actually there are 2 different approaches, because as you can see, there are the fixed keyword arguments. You can also have the keyword arguments. In the keyword arguments, if you were to use accumulator, Optuna will check this embedding that it again sampled from the list of available embeddings, and it would expect in the keyword arguments that you want to sample, or using this still hyperparameter optimization approach, it would expect keyword arguments to have the name of this parameter that you want to sample and the range for it, right? So for instance, if I were to say that, I don't know, angle embedding requires for instance, let it be the rotation gate that I want to use for the angle embedding, okay? So I can say in the keyword arguments that the rotation gate, for instance, I don't remember how it is called, but let it be rotation gate. And I can specify it from the set Ry, Rz, Rx. And it will then sample the rotation for the angle embedding from as a hyperparameter of this concrete embedding during the model searching, right? So it's up to the user to correctly specify what it wants from the software. But aside from that, when you add it, then it should work without any changes in the code.
I understand, how you're going to retrieve the method, but how you then synthesize all those unitaries that you're going to find into the higher level structure, which that is probably a more difficult task, how you align them together to solve a particular problem.
Yeah, okay. I think now I understand now. So when you're using accumulator, you're sampling the layers, right? In a ordered fashion. So I am sampling from the data embedding, then I'm sampling from the variational layer, then again the data uploading layer, then again from the. I mean, it's to be done, but you get the idea, right? So I've got the order of the gates I want to apply. I have the parameters for them, and so on, so on. So synthesis of the circuit is basically applying the layers because I've got the access to the constructors, right? So I can do it every time, applying them in the order they were sampled. Then I train such model using standard methods. So for example, some kind of gradient descent, and I evaluate the model basing on the data that I have from the user. That's
So you
the
would write
underlying
a
criteria.
template for that, yes?
Excuse
A
me?
template for that sequence you would have to prepare in advance.
Not really. No, it can be very general because I only have to specify the building blocks. I don't need a template, but the template is specified in the form of building blocks, right? Because the only thing that differs is the ordering and the number of wires, perhaps.
Okay. Thanks.
Thank you.
Yeah.
All right. There is one more question from GHN. Maybe you would also like to unmute. Or maybe I will read it. It appears to me that the Python framework is for pipeline task that works in sequential order. Have you considered the tasks of data analysis and the function, the items to carry out the tasks are actually not in timely synchronization by order? So this is the last question.
I failed to see, for instance, how classification would be a timely, could be considered a time-related task, right? Because if you are doing a classification, so a standard machine learning task, you don't have to restrict yourself to some time-related data points. For example, the moon is actually not at all time-related, right? You don't see a time here. So in that sense, I'm not sure if I follow the question, because in my understanding, there is no such restriction. But maybe you meant something different that I don't understand.
I try to elaborate my point a bit more, just in case that we have some misunderstood each other. And otherwise, it's just my mistake to point out my perspective or question to you. And it seems to me, could you go back forward to the timeline sequence of flow chart?
I know which one. Okay, I got it. This one, perhaps.
No, this one. The flow chart timeline.
Yes.
The sequence of the task.
Yes.
First you do this and you put in queue and the out queue and do the processing or classification.
Yes.
And have you considered that the part that's doing the classification actually, in your words, it's simulation, and in reality, is actually not that in timely to be that ready to catch up with the task that is queue number one. For example, the out of the queue data packet, data task to be classified is sequenced as number one to be processed and to be classified. But it's just happened that the number one data has not been processed ready yet, but the sequence number two has appeared already. And if it doesn't consider time, it would be the queue has been jammed.
Okay.
By the queue limit is unlimited.
I mean, let me clarify a few things maybe. First of all, there are no intersection between those. If you can see one, this is perhaps an graphical issue, not the issue of accumulator. This was done sequentially, but only because this is done on a single processor. So assuming that I have only access to a single quantum resource, right? If I were to use Optuna, because as I said, Optuna can be used in a parallel process the stuff parallel, right? So if I were to use two workers, for instance, then we could see two different models at the same time. I didn't in this very specific case, but in principle, it can be done. It should be even one should be even able to do it right now, especially since you specified at the beginning of the number of cores specified, right? So here. So in that sense, you don't really have to restrict yourself to do stuff sequentially, unless you have some other limitations as the access to quantum machine learning quantum resource in general, not machine learning, right? Does it address your question, or is there something missing still?
I would really appreciate that if you could elaborate further, because you mentioned single processor of quantum machine or classical machine, and would be the processor has the buffer limit or memory limit, the RAM size limit.
Yeah, so I absolutely agree. So the machine limitations when you run this software are just as present as in any other case. So if you don't have the resources to handle, for instance, several cores, then the machine would probably tell you, okay, I can't have 16 cores, I will use 8 because I have only 8 available. If you were to use it on a real device, then again, there would be 8 workers, for instance, on your local machine, all pinging the quantum machine in, I don't know, IBM servers, for instance. And if the machine, the quantum machine that you're trying to access is not available to you at the time, I would imagine that the workers will just wait for it to be able to access it, the resource. So that the standard parallel computation stuff. I don't know if what's to elaborate here really. I would imagine you would have to specify what really bothers you a little bit more, so I can.
Guys, unfortunately, I think we need to go to the next talk because we have more than 1 hour delay now.
Sorry.
So yes, that's fine. No, thanks for answering all the questions, but we really have to go to the end. Great presentation, Tomek. So thanks for that, and Krzysztof, if you are ready.
So welcome everybody. It's my great pleasure to give a talk during this workshop on quantum machine learning. So I will be speaking a little bit more from hardware perspective, since I am both physicist and electronic, and also a kind of computer science guy as well. So the title of my talk is Towards Quantum Neural Network Implementation in Semiconductor Single-Electron Devices. So I'm working on this topic with my company Quantum Hardware Systems, and also this was the topic I developed at Łódź University of Technology. So let me move on. Right. So I will briefly give us the current status of quantum technologies available. I will address the need of quantum neural networks. Actually, I will come back to some original ideas of implementation of quantum neural networks from hardware perspective. So my philosophy is from hardware to software. So usually it's opposite to most of methodology, since dominant methodology usually is from software to hardware. Then I will mention, I will specify some properties of semiconductor single-electron devices, since this is very promising family of solutions that can replace Josephson junctions that are currently in use, and as with Qiskit and other technologies. In this context, I will also mention about quantum graphs, and then I will give explicit solutions and equation for the case of two single electron lines, and this is because in the formulated quantum neural network problem, I have n interacting single electron lines. So this is just generalization. And then I will mention about something about nonlinearity, which emerges from quantum mechanics, that is a linear, which actually emerges in the case when in n-body system we only perceived one particle. So then this one particle is governed by a kind of nonlinear equation, and I will just mention the methodology behind such picture. All right. So basically, you all know the principles of quantum mechanics, which is encoded in a superposition of states. This is actually also a feature of classical statistical physics, that this parallelness is built in. And there is an unusual feature which is mostly reserved for quantum mechanics. That's a quantum entanglement. This is non-local correlations that expresses non-local correlations, and this is resource for quantum computation. And this is the resource which is used, which will also occur in quantum neural networks, and their possible, let's say, advantage over the classical neural networks. Then of course, if we design the technology from the chip point of view, we need to be careful about decoherence processes. And as you see, one of the paper by Daniel Loss, he from last year on semiconductor quantum dots, they start to do better and better, and they approach the lifetime of quantum states similar as in Josephson junctions that are used in IBM quantum experience. Then there is, of course, interference phenomena that occurs in quantum mechanics, and this feature of movement over many paths at the same time. In the context of previous discussions, I can also say that it's not surprising that quantum machine learning is a bit encoding, has similar capabilities to classical statistical physics expressed by classical machine learning, because somehow those theories are interconnected. Okay, let's move on. So basically, we have various types of qubits implementations, more than 20 existing technology nowadays. Here's the brief sketch of Josephson junctions that are used. So there is a superconducting nanowire interrupted by non-superconducting strip. So this is picturized by X sign, and then there is a possibility of tuning of physical states. So there is a quantization of energy levels in washboard potential given on the right. So this is the technologies which we are using mostly right now. Actually, right now we are using transmon qubit that is specified on the next slide. So before that, before coming to description of transmon qubit and then its reference to semiconductor single electron devices, I need to give a brief introduction to superconducting Cooper pair box. Essentially, we have a small superconducting island. On the top, there is insulator, and on the top of it, there is a bigger superconductor. And this small superconducting island is in proximity to metallic plate that is charged. So then this charge present on metallic plates push out Cooper pairs from this small island. So this incorporates this Cooper pair box that's specified here. But this system has had quite a lot of noise in itself. So then it was enhanced, and then the transmon qubit has emerged. So in a transmon qubit, you have bigger superconducting island, two insulator materials, and then there's another superconductor, and this is tuned by external metallic plate. So here, actually, electric field is used for controlling of the quantum circuit as well as magnetic field. So two fields are used. So that's this enhancement, and this qubit has quite low noise, therefore it's kind of commonly used worldwide right now. So there are various variations of this qubit. I'm not going to describe, but then there's also possibility of having this interface between Josephson junctions, or superconductor, insulator, superconductor versus semiconductor quantum dots. I will refer to this slide a little bit later in my discussion time. So what is the topic of my interest for today's presentation is chain of semiconductor nanowires that are in gray, and on the top there is a metallic gate that is separated by insulator. In such a case, you can define programmable two-dimensional metal lattice. So you can block the electron transport across certain paths. Actually, you can even encode a kind of like metric, like coming from, let's say, from general relativity. So you can create bounded states, but also when you look on the system closer, you can recognize certain injectors as inputs of your quantum neural network and certain injectors on the right side as outputs. So also this system can incorporate neural network as well. So this is quite unusual feature, which I'm going to discuss a little bit later. So this is typical artificial neural network. Essentially, I would say what is the essence of artificial neural networks is this interconnectivity of layers. It can also be later translated by strength of so if you imagine this is a physical system A, this is physical system B, then there is physical system C, and this is physical system D, then this interconnectivity also can be expressed by interactions. But what is the essential part of artificial neural network is that there is nonlinearity built in, and I will explain a little bit later how to come out with this nonlinearity in real physical system. Okay. Then next slide. Yeah, and then now people are having more and better lithography techniques, so they're able to build smaller and smaller nano-sized systems. So basically, we can attempt to encode a neural network that can be both classical and quantum by means of semiconductor quantum dots. They are very well scalable. So like the recent transistors, for example, there is interconnection between source and drain in the range of 5 nanometers. So this gives you possible big density of information that can be present in such systems. So I'm just giving briefly the insight into that. Yeah, so basically with given lattice, I can attempt to have a classical and quantum artificial life implementation, like kind of Conway quantum game of life. I can have a quantum communication and metrology and quantum computation. I will focus today on the quantum neural networks, and also I can think about implementation of hybrid classical quantum algorithms in that type of system, and of course I can translate other physical models to this two-dimensional lattice model. Okay, so if we see the current status of superconducting technologies, there is more than 20 already existing technologies. But from the point of view of really big industrial applications, the most serious seems to be superconducting technology that is already in use, and there is but there is a problem with superconducting technology that it has saturation of. It cannot be downscaled because the size of Cooper pair in a superconductor is in the range of 300 nanometers. So that's why you cannot make very small transport qubits. And this barrier can be replaced by semiconductor quantum dots, or so that they are already in big development. But of course, not yet they have exceeded the performance of superconducting Josephson junctions. Of course, you can also think about hybrids. So this motivates me to go for a quantum dots or for possible interface between quantum dots and Josephson junctions. And here is the scheme of possible quantum neural network. So by red dots, you have a semiconductor areas. So the electron is localized in those regions. And basically, the interconnection is expressed by orange. and on the top of it, there is metallic electrode that is separated by insulator. So these metallic electrodes, they control the connectivity of this neural network. So you can reprogram its shape quite dynamically. So that's a feature. And basically, having the injection of free electrons at the same time, then they can propagate their structure, and then they can arrive into detectors. So this is one of possible scheme, and then this problem becomes naturally the problem of quantum transport across the structures. Here there's something like layers, but this layers makes also a kind of complications from the point of view that those wave functions intermix. So you can also think about disconnecting of these interlayers. So the system becomes a little bit simpler in its description and its steady. Right. I will maybe answer to these questions at the very beginning, at the very end, about the curvature. All right. So let me move on. So this is my motivation factor, motivation starting point, and then I will just briefly give a scheme of methodology that can be used in its description. Then, if we talk about even from the picture from before, so let us see certain thing. So if we here on the right side, let's say, let us cut this interconnection in between. So let us make very big barriers by setting certain voltages to C1 and C2, C8 and C5. Then basically the system will start to be visible as single electron lines. And so they will be weakly coupled. Otherwise, the interaction between them, they will be strongly coupled. So now I will try to see from a physics point of view how to describe the systems in greater detail. So, okay, and this is on the next slide. So basically, the suggestion is that you have like in elementary particles, you have scattering problem. So you can have incoming particles when they try to collide or they're close to interaction. So when they are very far away, they don't see each other. So this is how you're supposed to see free inputs as free independent qubits or weakly interacting qubits. Then they can interact with big ensemble. I call it soup of n interacting particles that are controlled by some signals. And then at the output, you have free qubits that also follow the same pattern of inputs. So they are weakly coupled one to each other and also moderately coupled to this assemble. So this is basically the scheme of devices. So this is how to translate this problem to n-body physics, and then quantum physics, of course. Then there is also the case of simplification of a system from the left, when you, like as I already mentioned before, you have separated this the big soup of interacting particles into actually n-coupled inductively or electrostatically coupled single electron lines. Then you have the structure on the right side. So you have relatively weak interaction. And this is actually the concept of single electron wave function that is perturbed by presence of other electrons can be valid. On the left side, however, this perturbation framework is no longer that possible, especially in the medium area. So this is two pictures which you could think on. And of course, it's somehow better and simpler to start from the right picture. Okay, let me move on. Okay, so this idea of neural networks. So there was idea of neurons, artificial neurons is not that young. It's 2002. It was first proposed, but actually I could not come across big implementation of quantum neural networks among big players as Google or IBM. So that's also surprising. What is the obstacle in doing so? But because of potential of companies as NVIDIA and others, I think this hardware design of quantum neural networks is very important, both from applied point of view and also from fundamental science point of view. And also raising this question, how better is quantum neural network performance in relation to classical neural network performance is very important question. Okay, so now I just want to give you very elementary toy models because I don't want to float you with too many equations. So imagine that you want to implement AND gate. And that imagine that then you have position-based qubit, which means that it's or bit, let's say. So if electron occupies half of this space over here, it has logical 0, and in another part is logical 1. And then so you have 3 electrons in the semiconductor areas that are in yellow. And then if you place 2 other electrodes that are positively charged, then also you also can have so you have electrode system. So this is 1, 2, 3, 4, 5, 6, 7, 8 electrodes. And with such framework, you can implement AND operation. I just remind you as exercise. And then the first situation is thinking by framework or of classical physics and Coulomb interaction. So this is like charge balls philosophy. You can think about the solutions of this problem of specified here that will come. And here's the following scenario. So if there are 2 inputs and then electron is at the end, which incorporates logical 1, 1, that this will generate you 1. And here is negatively charged electrode. Then if electron is here and here, remember there's always repulsion between the charges of the same sign and attraction if the sign of charges is of opposite. Then if one electron, one input has logical 0 and another has logical 1, then you have 0 at the output since electrons is in this position. And then you can have a situation when there is 1, 0 at the input, and then you have 0 at the output, and then when there's 0, 0, and there's 0 at the output. So you can design such a gate with proper geometries in the framework of classical methodology, and then you can go for a quantization, and I will mechanisms, and I will give you description how to do it very briefly. So. Yeah, and I will come to with the questions on the next slide. In the meantime, I also mentioned that my methodology is very compatible with CMOS technology, cryogenic CMOS technology that develops very rapidly those days, and therefore it can be used by a semiconductor industry. So here is a position-based qubit. So which is between 0 and 1. So the presence on the left quantum dot is 0, and on the right quantum dot is 1. So here is this situation of this position-based qubits, and so this is position-based qubit expressed on the left side. And when you want to do a logical negation, you are using simply the fact that if you have charge in a box. In one box and another box, the charges will tend to be opposite with maximum distance due to Coulomb repulsion. So the system which is described here is natural expression of NOT gate that you can implement in devices. And also you have source and drain in transistors. So source can be recognized as one quantum dot and drain as another quantum dot. So that's how it's related with technology. Okay, so let me move on. Yeah, so you can express various gates and architectures in the framework of lithography techniques. Yeah, and then you can have also programmable quantum graphs, since you can, as remembering this lattice, meta-lattice, two-dimensional meta-lattice of quantum dots, as meta-lattice of nanowires, you can cut certain regions. So you can actually program quantum graphs in a real time. And basically, if you have a quantum algorithm expressed by a graph, I can translate this into physical signals. All right, so let me move on. Yeah, so and then there is a Vanir qubit this position-based qubit, which I mentioned before. So it's Hamiltonian, and so essentially it's two-dimensional. It's like spin like Hamiltonian. So there is energy associated with presence on the left and right quantum dot, and there is some Hoping term in between. So this is Hamiltonian for a single two quantum dot system expressing one position-based qubit, and this is related with eigenenergy qubit is commonly used because in typical eigenenergy qubit you are having the linear superposition of two energy levels, and this can be directly translated to this Hamiltonian or to this matrix that is basically similar to spin in a magnetic field matrix. And the translation is expressed by R coefficient. So here are wave functions psi1 and psi2, which are eigenvalues of Schrödinger equation for first and second energy level. And then there's integration. So basically this is very, you can go from position-based qubit to eigenenergy qubit, or from eigenenergy qubit to position-based qubit. So the minimum kind of expectation is that at least two levels of energy are occupied. So then this information is compatible in both systems. So you can also deal with various curvature of cables. And then what is interesting, you have a system of two interacting particles. This is expressed by such a Schrödinger equation. So this is the system. So we have confining potentials for first and second particle and interaction Coulomb term encoded over here. What is interesting that with bending of cables, there's a kind of like dissipative term that emerges. And actually, it can be formally translated into complex value vector potential. From physics, we have a real value potential, real value vector potential, but due to this non-zero curvature of the cables, this potential can become complex value. All right, and then in case of two quantum system interaction, two qubits interacting, you have such Hamiltonian. And so just to remind you, if you have any single electron lines, this picture will become more complicated. It will be like matrix 2 to the power of n times 2 to the power n. So this is just a kind of simplest case. So this means that basically quantum neural networks, it's quite difficult to model the quantum neural networks that has more than 10 inputs. So you need to use a kind of classical methodology to do it. All right. And then there's a prescription how to have these coefficients Q1, Q2, Q3, Q4 which express Coulomb interaction that are given over here. So basically we can incorporate. So the thesis of this work is as following. If you have a classical neural network, I can encode it in charge ball philosophy, and having this encoded in charge ball philosophy, then I can also quantize it and go into a quantum picture. But I cannot deal with more than 10 inputs due to the nature of complexity of system. Nevertheless, it can be expressed experimentally with as many inputs as you like. So that's also a feature of experiment that can go beyond theoretical picture. So I can also express basically any quantum of algorithms by equation 7, and then incorporate this in neural network. My thesis is even stronger. I would say that recurrent neural networks can incorporate most classical algorithms. And if I have a quantum recurrent neural network, I can most likely incorporate all quantum algorithms as well. Yeah, so there are some features of ground state. Maybe I will skip it, and then I will just to form you the final message. So you can also start the description of this problem in terms of classical Hamiltonians. So here's an example of some simulations done by student Piotr Miński from Łódź University of Technology. He did fellowships with Quantum Hardware Systems Company. And then basically he expressed OR gate by such Hamiltonian, classical Hamiltonian of two interacting particles. So here's effective potential, and then two particles were injected and the input. And then, so this is the framework, methodological framework known to people dealing with physics or mathematics. Then also you can do such things for XOR gate, also express classical XOR gate by terms of classical Hamiltonians, and then you can go for its quantization later. So, and then also there is interesting that two previous pictures, if you perturbed by noise, then you can have family of trajectories. And then actually this family of trajectories can generate you probability map. And if you use square root of probability, then you can have a kind of wave function generated quasi-classically. So this is like Nelson mechanics. So there are certain interconnections with classical statistical physics here as well. So I can just say that I can basically model both semiconductor quantum dots devices and also superconducting quantum dot devices in this framework. And there is a lot of work in progress. And just at the very end, I will mention how it happens that nonlinear mechanics, because the key argument against quantum neural network is that you can say that Schrödinger equation is linear. How are you supposed to get this nonlinearity? And here's a picture of two simulations of two charged particles described by one-dimensional Schrödinger equation. They are trapped in a box. So here are the cases before and after measurement. And then how it's possible. So if you have weakly interacting particles, then you can, for n-body case, you can have factorization of few wave functions of each particle. And then with proper integration, you come into equation 32 and 33. So basically there is a potential, AB potential, that depends on the wave function of another particle. And this potential will lead you to, from integral equation into integral differential equations that are as specified over here. So in that sense, you should expect that this chain of quantum dots in the framework of a single electron particles has nonlinear feature of nonlinearity that is very much needed in design of neural networks. So this was somehow described the simplest scheme. Maybe now I have a time for your questions or comments. So please, I'm open. Thank you.
Okay, thanks. I see that there are some questions from Sebastian. Maybe I will read it first. Why and what kind of curvature do you mean, and do you plan to use some symmetry patterns in your device? So this is the first question.
What kind of curvature symmetry patterns? So, okay, so I already used this device, which is given over here. Okay, so let me come back. So it's possible to model like gravitation center, for example. So you can build a metric. One second, where is that? You can build a metric. Yeah, so this is the slide. So you can program any type of two-dimensional metric you like, basically. So you can simulate kind of gravitation waves, or basically the system of interacting bodies. And what is also interesting, you can also let's say model the bounded molecules. So you can have certain charge over here that plays role of nucleus, and there will be electron that is unbounded orbit. So you can basically, with this system, you can implement two-dimensional chemistry. That's my message. Did I answer your question or not so much?
Yeah, it's enough. Thank you.
There is an MPI paper, materials 2024. So please just type MDPI Pomorski materials 2024, and you will find more reference, or I can send you this paper to you directly.
Thank you. And what with symmetry? Could you apply some kinds?
Yeah,
very special kinds of symmetry for
yes. I guess so, right? I can also polarize. So I can, for example, apply rotational symmetry by some voltages applied to it. So I can basically have a pattern of periodic or non-periodic pattern. It depends on your needs. So I definitely have such possibility, I would say.
Okay,
Is
and yeah, thank you. That was my question also for this, because you define weak and weak interaction and very weak interaction, but as I understand, at this level, at this quantum mechanical level, you just have a kind of electromagnetic interaction, just
well,
not.
the problem is that here on the right picture, if you have separate lines, you don't expect that the electrons will jump you from one line to another line. So in the picture on the right side, you can omit spin degree of freedom in description of electron or holes. Actually, it can be also for holes, moving holes as well. But in the left picture, you cannot ignore a spin presence. So the wave functions will intermix. So what consequences will you have? So you have three separate wave functions injected. When they propagate, some wave function of first electron will be partly present here, here, and here. So it can be fractionalized. First charge can be fractionalized at the output, right? And this is the same with second and third wave functions. So this will be complete intermixture of wave functions. So that's why this picture of strongly interacting single electron lines expressing quantum neural networks, this picture is, I would say, more involving theoretically. And also, if you are involved with n-body quantum system dynamics or even classical system dynamics, you know that n-body picture is without mean field approximation is challenging, basically. It's challenging in modeling and in analysis in general. So this system is will have this systems will have will be more complex. So I can analytically I can tell you I can pre-design quantum neural networks of the right system much more easily than the left-right system, because there's certain intuition of charge balls which I can incorporate in the right picture in a weakly interaction with these gaps in between. But this picture might be broken in the situation on the left side. So that's not that easy, but it's a nice research for future, I would say, right? So that's nice vision for some future site.
Okay, it's just one last question, sorry. Because you said something about this holes with electrons. It's possible maybe take some effective kinds of particles different than electrons in this device?
Absolutely, because let's say what is electron is lack of hole is a lack of electrons. So this hole can move back and forth. Let's say, okay, so you can inject holes as well. So they have all features of electron, except the fact that they charge the whole charge is opposite of the electron. The spin of hole is opposite of electron. And when the electron meets with electron and holes meets, they recombine. So this is like annihilation. So in a very real way, hole is almost like antiparticle to electron. But from equations point of view, the equations are actually almost the same. So the same concepts will apply, basically. You can have also a situation when you inject hole and electron. You can also deal with such situations. There is some study of Dirac Q company from Australia, because they're one of the best in the world in this direction, research direction. So they also start to use hole more often than electrons, actually, for certain experiments. So both particles are possible, but it's rather recommendable to use only one of them. So it's better to decide to use holes or better to decide to use electrons.
Yeah,
it's also
because I just remember that you can have, for example, perovskites that the topological information about holes and electrons can give you some new opportunity to do something more with that. So yeah, this is very, very interesting.
Well,
Thanks.
electrons and holes, they occur in Andrew-bound states in Josephson junctions, so they're both present. So if you have equations, Bogov-Dijon equations for Josephson junctions, then you can. By the way, if we already touched the Josephson junctions, there is a lot of nice work by D-Wave company expressing superconducting classical Josephson junctions using. So you can implement classical neural networks on Josephson junctions. It's already done. But what is the feature of this work is small size of neural network and possible quantumness. So there are two things that I can address. But even if this network doesn't fully work in deeply quantum picture, it can still be parameterized, used for a quasi-classical neural network. So that's a nice feature of that. But of course, a quantum neural network will have better possibilities, and especially when you integrate it with, for example, with quantum detectors, then if you have some information storage in quantum detector, it cannot last too long. It needs to be pre-processed. Yes. So this is one of area of application of quantum neural networks. Did I answer your question?
Yeah, thank you very much. It is very, very interesting for me. Thanks. And we probably has also a question from Jacob. So
Yes,
maybe.
there is one question from Jacob. The question is, how would your solution compare in terms of performance and function with optical neural networks or neuromorphic chips?
I would say I somehow already described neuromorphic chips more or less in that way, because okay, you can also couple this system to some other systems, so there could be some information storage and so on. So somehow this methodology expresses neuromorphological systems. What was the second part of the question? Paweł, what was
optical neural networks?
Optical and neuromorphic chips.
Optical. Well, there is a competition, so people start to go. They can use photons instead of electrons. So there's a competition. I would say the photons has a okay, so like there's a quantum optics in quantum information processing present, right? And the problem is that it's hard to make two photons to be interacting with each other. On the other hand, they can interact, for example, via a nonlinear medium, for example. But on the other hand, they have long time of life. On the other hand, electrons are strongly interacting and are scalable, but they don't have very long time. So there are advantages and disadvantages. So it's hard for me to answer this question in greater detail. I think one needs to do more research on that.
Thank you.
Okay, thanks. All right, I don't see more questions. So Krzysztof, thank you once again. First of all, for the great presentation and for answering all the questions.
Thank you.
And yeah, that was the last talk for today. So I would like to thank everyone for coming, for participating in discussions. That was quite interesting. I believe we've learned a lot. And yeah, as I said, we'll do our best to publish the video recording on our YouTube channel. And we hope to see you soon next time on our next events. Thank you. Have a great weekend.